can just go to the chat room and respond if you can hear me loud and clear. Just go to the chat room, respond by saying good morning. Emmanuel Devon, good morning. Yes, I can see that from you. Zoe, good morning. Zoe, good morning. Yes, I can see, we can all hear me loud and clear now. I want to believe that because I can see our responses already. So good morning. And some persons have said that before. Raphael Aidoho, good morning. Ogujobi Mary, good morning to you. Good morning. Yes. Oh, good morning, Okobong Epedoro. Good morning. Good morning. Good morning. Yes, I am just laughing. I'm just smiling here because this is a powerful good morning from a powerful person, right? Good morning. We're all powerful persons, right? Part of my words. So right now I believe we should just start the class while other people will join us as long as we've started, other people will join us as the class goes on, right? So I want to prepare our mind for this morning. I have said this before other people join the class, and I'm going to say it again, right? This class is one of the most, in short, I want to say it is the first and foremost important, or okay, let me use the one of the most important class that you can never miss, that no one should ever miss. If we are in the journey or on the journey of technology, as the case may be, you are in computer science engineering, you are, computer software engineering, you are in networking and system security, you want to go into AI, you want to go into technology, you want to go into cybersecurity, you want to go into anything at all, as the case may be, in as far as it is science oriented, in as far as it is technological oriented, in as far as it is business oriented, anything at all, this course, Logic and Linear Algebra, is very, very important and very, very, very useful. Very, very important. So I don't want us to take it lightly. I want us to take it with all of our strength. I want us to learn every bit of this thing we can learn in class today. We've got a powerful lecturer, a powerful trainer that is going to take us through this journey today. So without much ado, without wasting much of our time, I'm just going to introduce, and I want everybody to join me. Make welcome to class our lecturer for today in the chat room. Can I see your welcome in the person of Ebedoro Okobong Gregory? That's our lecturer for today. Ebedoro Okobong Gregory. Can you go to the chat room and welcome our lecturer for the day, Ebedoro Okobong Gregory? Ebedoro Okobong Gregory, welcome to class, and over to you. Over to you. Just take over from there.
Okay, thank you very much, the host and the co-host, and every one of you out there. He has just called my name. My name is Ukobong Ebedoro, and I'm so happy to be with you all as a tutor to this particular course, MTH 101, Logic and Linear Algebra. Good morning to everyone. We start right away. I don't know if the host or the co-host is listening to me now. I wish someone out there can share the course material because I think I'm using phone now. I am not so familiar with how to share course material using phone. So if the host and the co-host is listening, I want the response on whether they'll be able to share the course material so that others can follow as we speak.
Okay, this is it. You can just go ahead, just go ahead in speaking. Can you hear me? Just go ahead.
Yes.
All right, just go ahead in speaking. I will get to display your slide, right? Just go ahead. Keep on speaking. I will display your slide for you. But
Oh, okay, okay. So is there any way you can display the slides here?
yes, that's what I'm saying. I will display it from my end here. I will display it from my end here, but you go ahead and speak. Go ahead and talk. Go ahead and talk while I get the slides ready for you.
Okay, please. Yeah, okay, okay. Please do share the slide as soon as possible because even me also, I will also rely on the slide so that I can guide myself on the way I flow.
I should share the slide with you. Are you with me?
So we continue. Logic and linear algebra divides into two. Logic, the part that linear algebra. Okay, logic part deals with a way of analyzing statements and sentences to make conclusions, numerical calculations on some topics, such as the matrices, such as the permutation and combination, and the rest. Okay.
Are you still with us? We can no longer hear you say anything. Are you still?
Yes, I want to try to see if I
So
can.
I share the material with you.
If I can share, please, can you share the screen as soon as possible?
I'm doing that already. Just hold on. I've shared it with you. So just hold on.
Okay, please, because there are some statements we want to use for some analysis here. So I want every one of us to flow together so that we can make some reference to some statements on the slides, please. I have tried on my end here to share it, but it's telling me error. What have I done with you today?
Can you see my screen now? Hello, can you see my screen?
Yes.
Okay, so are you okay with this, or should I make it more
Yeah, just go. All right, very good. Just go down to the next page.
Okay. So, are we good?
On my end here, it's still showing that first page.
Okay,
here,
I should just move away from there, right?
Yeah, just move to the start. This is just the
All
first.
right, all right.
Hello? Okay, the objectives are here. Just move on to when we have propositions.
When we have what?
Proposition, the next page.
Okay.
Oh, very good. Okay, let's start here. We, like I said, the course is divided into two main areas. The part that deals with logic and the part that deals with the linear algebra. And good enough, we plan to finish up the two parts together today, if time permits. And we want to start with the area of logic now. Okay, logic is, like I said, is a part of this course that deals with the analysis of statements, analysis of sentences to make conclusions. Okay, we want to start with what we call the propositional logic. Okay, in brief, logic here is divided into two parts. The propositional logic and the part that has to do with the predicate logic. Okay, what is proposition now? A proposition is just like a statement, a verbal or a written sentences that can either be true or false, but not both. Most times in our life, we get into such arguments whereby somebody make a declaration that something like this is this. Okay, and not give a room for someone to say, no, you are wrong, or yes, you are right. But it can be both of them. So if you come across some statements like that, know that the person makes what we call proposition. Okay, for example, let's run through a few of those sentences you have here. Okay, we have the person that says that Lagos is Nigeria. The second one says that 9 is an element of 7, 8, 9, and 10. The third sentence there says, are you a Nigerian? The fourth says x plus 5 equals 9. The fifth sentence says, come out. While the sixth sentence says, what a great day. And the seventh sentence says 3 plus 4 equals to 9. So I want to every one of us to think through these sentences now and suggest whether or not they are proposition or not. Remember, I said earlier that a proposition is what? It's a declarative sentence that can either be true or false, but not both. So the list of sentences here that I make here, I want all of us here to just think through it and express their mind on how they feel the sentences are, whether they are due to be called proposition or not. Please, if you can hear me here, if you can hear me out there, just type, I'm here. I want us to run a kind of interactive class. I don't want to be the only one that speaks here and not knowing whether the audience.
Sorry about that. My network.
If you are listening.
Yes, I'm with you. My network just logged me out, so I'm back.
Okay, please bring back the screen.
Yes, because it's on already. It's on. Check.
Okay. All right, please. I want the audience out there to type "I am here" so that I will be confident that I'm speaking to people, because I want us to understand.
Yes, you can just go to your chat room and check people's response. People are responding already in the chat room.
Damilare, very good. Okay, I see. I'm seeing I'm here. Very good. So what I said in essence is that a proposition can otherwise be called a statement. But in that case, we are talking about what? A declarative statement, something that someone declares that can cause for a judgment to see whether the statement is either true or false, but not both. So we call that a proposition now. So there are lists of statements here or sentences here on the whether they are qualified to be called proposition or not. Okay, in the absence of this thing now, any response now, I would move on. Okay, if you look at statement 1, which says Lagos is in Nigeria. Lagos is in Nigeria. That's a declaration. That's a declaration. So someone out there can say, okay, your statement is a proposition now. So let's look at statement 2 that says 9 belongs to, or 9 is an element, or 9 is in the sets 7, 8, 9, and 10. That one is also a proposition. Why? Because it's a declaration. It's a declaration. Okay, but let's look at the sentence 3 that says, are you a Nigerian? Are you a Nigerian? If I may ask, if someone just said that, are you a Nigerian? I don't think you will be able to tell this person you are wrong or you are right, because it's just a question. You need to just answer either yes or no. So in that case, it's what? It is not a proposition. The person has not declared anything, so you don't have any argument to make there. I hope you are following. Okay, let's look at sentence 4 that says x plus 5 equals to 9. X plus 5 equals to 9. Okay, even though that one looks like a declaration, there is something there, x, which is unknown. So the truthfulness or falsity of that sentence depends on what? The value of x. So in that case, it is never a proposition because of what? That x. Because if I say x plus y equals to 9, and you say, it's because how do you know it's false? The value of x needs to be specified before it becomes what? A proposition. I hope it's clear. Okay, let's look at sentence 5. Sentence 5 says, come out. I think that's a command. It's a command. It doesn't cause for arguments. You cannot just say it's true or it's false when someone says come out. So it's what? It's not what? It is not what? A proposition. It's a command. Okay, let's look at sentence 6. Sentence 6 says, what a great day. What a great day. What a great day. So I want someone to just tell me now that whether it is a proposition or not. I leave sentence 6 for someone to respond. Is it a proposition So if you think it's a proposition, type yes. If you think it's not, type no. But let's switch to sentence 7 that says 3 plus 4 equals to 9. 3 plus 4 equals to 9. All of us know that is a blatant lie here. But what happens to it is what? A proposition, because a declaration. Imagine you have a child that is in nursery school and he come back from school and tells you 3 plus 4 equals to 9. You only tell the person you are wrong. Yes, that is what? A declarative sentence. So it's what? A proposition. So in general, what I can say here is sentence 1, 2, and 7 are propositions. I leave sentence 6 for you to judge, please, so that I would be able to know whether you are following or not. Please type in the comment section yes or no. Yes, if you say that sentence is a proposition, or you type no if you think that it's not. Okay, so we have 2 types of proposition. Just like we have in sentence, because proposition is just a sentence. I think in English, we have and what again? Compound sentence. Very good, very good. Simple sentence and compound sentence. Yes, it happened like that in proposition. We have simple proposition and what? Compound proposition. A simple proposition is just a list of statements, like the ones we make here. For example, Lagos in Nigeria is just a simple proposition. It's just a sentence. Okay. So, for example, we have the student's intelligence. It's a simple provision. So we use small letters, something like P, Q, and R. To denote provisions. We won't be able to write all the sentences down. It might be a compound sentence that is so long, so you won't be able to write all those things down. So in that case, we use some symbols to denote them. So in logic, we use small letters P, Q, R, S to denote what? A proposition. So take note. Please go to the next page. All right. So I have mentioned that we have 2 types of proposition, which are what? The simple and the compound proposition. Now, so what are compound propositions? Compound propositions are what? Are a combination of what? 2 or more simple statements. So if you combine 2 or more simple statements, what you have there is what? A compound proposition. I am also referring to proposition. In short, in this class, I'll be using them interchangeably. Both statement and proposition are the same. Okay, so if I say statement, just understand that I'm talking about what? Proposition. Okay. Now, so a combination of 2 simple propositions is what we call what? Compound proposition. For example, x plus 4 equals to 9, and today is Friday. X plus 4 equals to 9 is a simple statement on its own. And today is Friday is also another simple statement on its own. So if I say x plus 4 equals to 9, and today is Friday, that means I have join the 2 parts together to be what? A compound statement, a compound proposition. Okay, and what enables us to join them together is what we call connective. Connective are words or phrase which enable us to join propositions together. And the connective, what we have here, we have here a connective like negation, we have a conjunction, we have disjunction, we have implication, and also have what we call equivalence. We will go through all of them in this class. So take note, like I said, that connectives are those to join 2 or more sentences together. Okay, so let's start with the connective that we call the negation. Please, as we continue, I want to be sure that you are listening. If you are listening, just type here, go on. If you are listening to me, type here, continue. Or if there's any question you want to ask, you can ask. If there's anything you do not understand by those explanations or from those explanations, you are free to ask on the comment section. But if you have understood, just type here, continue, so that we can move on. We have a lot to do today. I want your response. Am I here alone?
Someone has chatted in the chat room already. Just go to the chat box.
All right. I can see you continue. So let's move on now. So, like I said, we want to explore how connectives work. We want to explore the meaning of connectives and the type of connectives. Okay, so I've already listed the type of connective you have here. Is there on the screen? We have what we call negation, we have what we call conjunction, we have disjunction, we have biconditional statement, we have conditional statements and biconditional statements as connectives. Okay, let's start with negation. Negation is just a way of reversing the meaning or the truth value of a sentence. If you apply a negation to a statement, if that statement was true, the statement will come false. And if that statement was false, that negation will turn it to false. In negation. For example, if I say Nigeria is a rich country, if I say Nigeria is a rich country, which is a proposition here, let's assume that I use P to denote that statement. So if I use negation, if I say negation of P, that means the statement will become, it is not true that Nigeria is a rich country. Okay? All right. Let me pick another statement now. Let me say that there's a statement that that senator is not sincere. That senator is not sincere as a proposition now. So if I use negation on that proposition, the statement becomes, it is not true that the senator is not sincere. I believe you are following. So we call that negation. Okay, after that, there's another connective here that we call conjunction. A conjunction is just the joining of two or more statements together using and. So whenever maybe you heard about conditions that say this thing happened and the other one should happen, what they use to join those statements together is what we call what? The connective is what? Conjunction. For example, I believe all of us have an idea about the mission in tertiary institution when someone wants to seek for mission now. Let's say the institution says that someone must score JAM 100, and the person must also have it. Okay, so they use is a conjunction. And if you want to seek for admission, they will access the statement differently and now merge them using and. So it is if you pass through the two conditions that will enable them to admit you. Why? Because the connective was and. Okay. So listen. All right, so conjunction is just joining of two statements together using the word and. And the sign, the symbol of that conjunction and is just like inverted V. So if you have two statements, P and another statement Q, and you want to join them using the connective and, you just type P and then put that symbol, which is just like an inverted V, and then put Q. And don't worry, as we progress, we will access how those connective work in their respective truth table. And what you have to note from now on is that every statement has what we call the truth value. The truth value is a result of a judgment on that statement. For example, if I say 5 plus 4 equals to 20, okay? And every one of us here know that that is a false statement. So that particular statement will carry the true value F. We use capital F to denote a false statement. And we use capital T to denote a true statement. For example, a proposition now. And if you want to access the true value of that proposition, automatically, you all know that that is true. So the response to that will be what? Capital T, to denote that that statement was true. Okay? Right. So as we progress, we look at what we call truth table. Truth table are where the true values of those propositions are reflected. Okay. A connective called disjunction. Disjunction. A disjunction is also can also be okay. It's the joining of two or more using the word or. So if there are conditions that says if you do this or you do that, and that connective look like V, the symbol, then example now, let's say I will say x plus 4 equals to, okay, 5 plus 4 equals to 9, or today is Saturday. In that case, the or that we put there as a connective is what will stand in between the two propositions. For example, if you use P to denote the first statement, I use Q to denote the second statement, the compound proposition will be what? P or Q. P said, after this slide, we'll look at the truth tables. Okay, we also have what we call conditional statement and biconditional statement. So we will leave that one to the next, okay, to the next pages when we want to access the truth table properly. So move on. Let's go to the next. Let's go to the next. Slide. Please, if you are listening to us, type continue. If you have any question regarding that, ask. And of course, as we progress, we will have some exercises that you can be practicing as we run the course. Yes, there are some questions I'll be asking, and you answer me to show that you are following. And if you are not answering it correctly, we can stand there and look for a way to help you understand better. So if you have any question, you can ask. If you want me to continue, just type continue. Let's move on. Okay, before we go to truth table, we want to look at what we call parentheses and grouping in logic. Parentheses and grouping in logic. You know, in logic, we deal with so many statements and connectives. So in that case, if we join two or more words together, there are ways you may find some of those symbols confusing. So what helps people to flow better is the use of parentheses, the use of brackets. Okay, so just like in normal calculation, in normal arithmetic, in normal algebra, that we have BODMAS, which directs an individual to which part of the mathematics he has to access first. We also have the rule here in logic that enables us to go through our own analysis properly without making mistakes. If the first thing you should do is to work on brackets first. You work on brackets first. You know, Bodman says bracket open before division. Very good. So that is a rule in normal arithmetic. Okay. So in terms of logic, we also have the rule. The rule says what? That you should work with what? Bracket first. Work with bracket first. If you have a bracket, and then after that you go to negation. We've talked about what negation is. Yes, negation. You want to reverse a statement. You work with negation. And after that, you work with the conjunction and disjunction. We've talked about what conjunction and disjunction is. The only thing that remains is to work on the truth table for those connectives, which we will do in the next slide. So the next thing is to work on the conditional and the biconditional statements. We will look at that too. And again, in case of unclear cases, a case that there's no bracket at all. Why you show these rules? And before we end this class, I strongly believe that you will understand how to access the truth value of a compound statement. So the reason why this rule is made up is because of those compound statements, which may look a little bit cumbersome if you cannot know, you do not know when and when to place your to start your analysis. Next page. Next slide, sir.
I've done that. It seems your network is
Are you
lagging.
there?
I've done that since. It seems your network is lagging.
Okay. Don't worry, it's here already. It's here already. Thank you very much. Okay, I was talking about truth table. We have it here before us now. Like a truth table is a table which displays the true value of a statement across different cases. A truth table is a table which reflects the truth value of statements across different cases. Okay. Now we have the truth table, and we want to evaluate some compound statements and simple statements, and we also work in terms of analysis of statements. Don't do that. Saying something. Okay, so the first thing you have here is the truth table for negation A. If you look at A, you will see P and you will see negation of P. Please, that sign that looks like S, but it's horizontally, is a sign for negation. So, for example, if P was a statement that says Nigeria is a rich country, and on the other side, you see negation of P. Now, you will see T and F. T means true, F means false. So what the first table does is, it displays the truth value of a particular statement and the possible result. So if I make a statement, the possible results can be, and if you negate it, the truth becomes false and the false becomes true. Statement 2, okay, the table 2 is for conjunction, the truth table for conjunction. Okay, the first part of that table B is P. P is what? Is one particular statement. For example, 5 plus 4 equals to 9. And Q is a different statement. For example, today is Monday. Now you want to join these two statements together using the word and. You see in the third column, you have P and Q. Like I said earlier, that sign that turns B upside down is what we call and. So now we say P and Q. That sign say P and Q. Now we want to join these two statements together now using and. So please listen carefully so that if you want to work on things like this, you understand. These things have their own rules. It has their rule. If you join two statements together and then go to the resulting statements to analyze them, there are rules you will have to apply for you to make a correct result. Please give me like 1 minute. I will be back now. Give me 1 minute. Please give me 1 minute. Okay, thank you. I'm back. I'm sorry about that. There is a small child here that is giving me a lot of headache. Okay. What we were saying is about how to construct a compound statement using the word. Now down again to the meaning of the table. The table B is what I'm talking about now. So table B has two statements, statement P and statement Q. Remember, I've said earlier that and are those small so that we will not be writing. So we use this letters now. So let's say P is a statement and Q is a different statement. And I want to join them together using and. So what we do is if you use the first statement say true and the second say true. If you join two statements together, so the first, you see the first row of table B, the first row of table B is true, true, true for P, true for Q, and true for the compound statement P and Q. So the thing is, what is the rule that we apply that enable us to arrive at that P and Q is true? When P is true and Q. I have made this statement to. Okay, I have made this statement earlier. That let's say school is for you to have jam at least 100 and also for you to have to pass WAEC with credit, with 5 credit. Now, if you want to go there to seek for admission, what they will do is to access your own credentials to check if you have passed those conditions. Good. So what happened be true before the entire thing is accessed to. So if you go to the admission unit and submit your file, they check that, okay, you have passed the UTME, okay, true, and you have passed the WAEC, true. They will access that the entire admission process is what? True for you. I believe you know that. Okay, now let's go to, and the second one is F. Then the P and Q is F. Why is it F? The reason that is F is because just with the same process I'm talking about now, if you pass, let's say you pass the WAEC and you do not pass JAM, they will access the entire thing as false and the admission will be denied. Okay, become false. If you say false and true, it become false. Why? You only pass one condition. It's only one condition that is true. The other one is false. So because of the meaning of the connective and can only be true if the two statements are true. And Q can only be true if P is true and Q is true. Apart from that, it will be false. And then look at the final row. The final row say if, and P and Q is what? If. Good. Just imagine that you did not even have jam. I didn't even pass away. This particular thing is used in those in that make some this software analysis. It's used very well in computer science logic. So they use that to access some entries. Let's say there's something you want to access. So the conditions that is being passed in the system, if all of them, if they are using and if all the conditions are not passed, you'll be denied entry or access to the system. That is what happened in most computer reason. Okay, so we now go to all. That is table C. We now go to table C, which is the truth table for disjunction. Like I said, disjunction is the use of what? Or. Is the use of what? Or. Now, what happened to or? If they say or, it means that if either of the statements is true, that means the entire compound statement is accessed to be true. I repeat, whenever you hear or mean what? Or mean that if any of them is true, that means the entire P or Q is true. For example, like I said about admission, if they change the condition of admission and say the person must have called credit, okay, the person passes YH. So in that case, if you have any Q, would always be true, is true. P or Q will always be true, provided any of the individual statements is true. I repeat, P or Q will be true if any of the simple provision is true. Okay, let's go back to that table now, the table C. You see, the first row said that P is true, Q is true, and the P or Q is true. Good. Even if you get both the condition true, as long as what? One of them is already true, the result is true. So the second one says true, false, true. Why is it true, false, true? One of the conditions is true. So true, like I said, as long as one of them is true, the result will be what? True. But the last one is what? The first statement is false, second statement is false, so everything will be false. Like I said, if they say, okay, if you must have an admission, you need to have WAEC or you pass JAM. So you now go, you don't have any of the WAEC or JAM, so the admission you will not have it. That's it. Okay, the final, the truth tables D now is truth table for this particular provision now. Okay, I want to explain this one. I want to explain the D truth table now. D truth table is just an illustration on how we construct truth table for compound statements. Like I said, we may have something, the compound statement that consists of so many long arguments. So we work like this. We take each of the statements individually per column now, and you follow up how the statement is, and then join them through the connect. For example, now this particular one says, no, excuse me. It's okay, it's okay. Okay, so sorry about that. Let's go back. So now we have the P or in bracket, we have not Q, and Q. So what we do is, like we said earlier, that we work with brackets first. Work with bracket first. So you look at the argument in the bracket. The argument in the bracket is what? Not Q and Q. So what you need to do there is to access not Q first. That is why when you see P and Q are the possible outcome of those two statements. They are not as a result of any connective. You are just putting that true, false, false, true, false, because those are the possible combination of those two statements. But the next column, column 3, which is not Q, is as a result of a connective not that applies to Q. So if you look at that particular column now, you will see that the not act on what? Q, which was again, the not act on what again? Act on false here and become true. And if you check through those true value, whatever a negation is applied to, it changes the original value. So there is to still work on that bracket, not Q and Q. So not column and operated with the not Q column using one and. Okay, so you will see that not Q and Q, Q, when Q was true and not Q was false, the not Q and Q is what? False. So we use that same operation to work on the entire table. We use the same. What I want you to do now is, if you check now, you see exercise. The exercise says construct truth table for the following proposition. Construct a truth table for this proposition. And the proposition is what? P and in bracket, not Q or Q. P and in bracket, not Q or Q. Please, I would really appreciate if someone can share a sheet of paper and try to work on that exercise. It's not difficult. It's just something you can just look through and apply those connective and then get the result done before we even reach like 2 minutes from now. Okay, please go to the next page. Next page, please. All right, we now go to what we call the conditional proposition. The conditional statement, or we can call it implication, or we call it if-then statement. Okay, and we call it implied statement, and the sign we use is implied. Now, what does implied statement mean? An implied statement is a kind of statement that is if something like this occur, then the other one must occur. Keep it. If something like this occur, that means the next thing that occurs should be the other one. Okay, time for now. Today is Saturday. So someone will say, if today is Saturday, then tomorrow is what? Sunday. That's how the implied statement works. If the student studies hard, then he will have an A. We call that implication or a conditional statement. What happened is the statement P and Q has name in this case. One is named the hypothesis, and the other one is named the consequence. So once you know the true value of the hypothesis, that means the true value of the consequence is also known. Okay? So the knowledge of the consequence depends on the knowledge of the hypothesis in the implied statement. For example, if Akwa Ibom State, so you knowing that the place in Nigeria automatically tells you that what? That place is what? Is in Africa. Are we following? So we call that what? If-then statement, or we call that implication, or we also call that a conditional proposition. Take note. If he study hard, then he will make an A. If Abuja is in Nigeria, then Abuja is in Africa. Okay? So we call that what? An implied statement. Okay, see example. Example here says, if this month is January, then next month will be what? February. So the first sentence here, this month being January, is what we call what? The hypothesis. And the next month is February is what? Another sentence, which is what? The consequence. Okay? P implies Q, or if P, then Q is true, unless P is true and Q is false. So in a truth table, all possible combination with P and Q will be true. The only false will come if the hypothesis, the only false will come if the hypothesis, oh God, hold on. Hold on. Everything will be true unless P is true and Q is false. Oh, now let's look at the other one. That is okay. The biconditional statement, we call it if and only if. It's a form of implied statement. However, in this case, the P implies between the conditional and the biconditional statement. The conditional statement is one-sided. It's one-sided. We have the antecedent and the implication. Okay, so once you know the antecedent, you know the implication. Now, but however, in the case of biconditional statement, both of them are hypotheses, and both of them are also consequence. So we also say P implies Q, and it's also implied by Q in terms of the biconditional statement. And the symbol that we use is a double-faced arrow, or a double-headed, a double-side arrow. Okay, remember, in the other one, we use one-side arrow to show you that the P implies Q. Once you know the value of P, that means Q will not be difficult to know. If you study hard, you have A. If today is Monday, tomorrow should be Tuesday. Okay. If where I'm standing is in Nigeria, that means where I'm standing is in Africa. Okay, as simple as that. But in terms of biconditional, if you statement point to the other one should also point back to this particular one. So it has a kind of you give and you all take. Okay, so let us go to the next page so that we can know how to access the truth table for the conditional and the biconditional statements. The audience, are they listening? Please, if you are listening, just type continue so that to be order type continue, or we can just type I'm here so that we can continue. Okay, so let us look at the truth table for the conditional and the biconditional statements. Let's look at the truth table for the conditional and the biconditional statement. For two statements, let me be specific now for two statements. If you want to construct a truth table for two statements using any connective, what you should do is the first thing is to write down the first and the second statement in terms of symbols like P and Q. Of course, I told you that you cannot use the long statements. You just have to use a symbol to denote it. And most we use symbols P, Q, R to denote them. So if what you are working on contains two statements, just write down the two statements in symbolic way, like P and Q. What you should do is to think about the possible combination of their true values. Yes, you don't need anyone to tell you that. Think about, okay, what are the possible combination of these two values? For example, now, if I make two statements, let's say you do not know the outcome of the statement now. You don't know the outcome of the statement now, whether it's true or false. Okay, but you may just suggest what may have happened about the two statements. Look at how you think here. You will say, okay, that means if I'm making two statements, the first and the both statement may be true. That is why you see here P, T, Q, T. You just try to assume what must have happened to the statement at the end if you want to access it. So the first may be true, the second may be true. Apart from that, the first may be true, the second may be false. That's why you see the next row, you see true, false. Apart from that, the first statement might be false, second might be true. That's why you see FT, the first F, second T. And after that, both of them may be false. That's why you see FF. So those ones, you are not accessing anything. You just think through the possible combination of the two statements. Apart from these four, apart from these four combinations, there is no other combination you can put here again that exhausted the possible combination. So anything I'm putting down is just analysis now based on the connective. So the first thing is to do what, like I said, first thing is to do combination of the two statements. Then the next column is to do what, where you want to apply the connective at hand. So the first table here, you see first column P, second column Q. Now the third column is P implies Q. That is when you have allowed the two statements. Okay, you have allowed the connective to act upon the two statement or to join the two statement based on that particular connective or based on the this order of that connective. Okay, here now I have said earlier that P implies Q can always be true, except if P is true and Q is false. P implies Q is always true unless P is true and Q is false. If you look at that first table, you will see that true, 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 false, false. So the rest is false, true, true, false, false, true. Okay. All right. Let's look at the table. Table 2 is also table 2 is a conditional statement that is P implies Q and also implied by Q. Okay, like I said, the first thing is to do what? Put down P and Q and put down the possible combination of those two statements first. Then after that, you join the two statements based on the connective of interest. In that case, the connective you want to use now is what? The biconditional. Okay, so if you see, the biconditional will be true, will always be true, except for the cases that their truth values are different for biconditional. So if their true value are the same, the true value for statement A and B are the same, that means the compound statement will be true. But any difference, whether it's false, true, false, the result will be false. That is what you see here. When we have P is true, Q is true, the P implies and implied by Q is what? True. But when we have the P is true, the false, the Q is false, we have the false. When we have the P false, Q, the first statement is false, second statement false, the outcome of the compound statement is what? True. So that is it. For the third table, which is table C, which is the true value for P or not Q, if you see a compound statement like that, you don't have to be afraid. There's no difficulty about it at all. Just pick the statement one after the other and apply the connective appropriately, paying attention to the parentheses order we've talked about previously. Yes, you have to think through it. If it's not clear, you work from the left. Yeah. So please, you need to go back to that particular page and try to study the order of operation if you want to work on a compound statement like this. Okay. All right. Go to next page, please. And there's an exercise here anyway. We have an exercise here that you construct a truth table for P and not Q implies P. So you can try this particular truth table construction so that we understand if you are following or not. Please, next page. Next page. Next page, please. Okay. All right. We have here we call tautology and contradiction. Tautology and contradiction. All right. So tautology is just almost an opposite to contradiction. Anyway, it's just an opposite anyway. If you have a compound statement that is always true for all, it's always true for all possible combination, the truth table is what we call what? A tautology. And again, a contradiction is also a compound statement, but in this case, the result for truth table is always false. So if you have an argument or if you have a truth table you are constructing, and you find out that at the end, that particular column of that compound statement is false throughout, and no other thing is in the column, we say that that column is what? That statement is what? Is a contradiction. But if you have a statement you are constructing, a common statement, and at the end you see that for that particular column, everything is true. Everything true. We say that that particular statement is a tautology. So a compound statement that is always true for all possible true values of variables is what? Tautology. And now there's an example here that says, show that P implies P or Q is a tautology. And you also have to show that not P and Q or Q is a tautology. So you have to show this in anyway. Okay, for contradiction, we say that you should show that P and Q or not P, a construction of a truth table. Yes, it's a normal truth table construction. But in the end, you will just see the result. If at the end the result is true, all true. Okay, in this case, this is F across all the possible combinations. We say that that particular statement or compound statement is a contradiction. So for this particular one, we have found a solution to A. And at the end, we see that P implies P or Q is a tautology. Why? Because that particular column, the column of P implies P or not Q is true. True for all possible cases. So in that case, it's a tautology. For the second one, the P and Q not all, okay, the P and Q or not P, we found that entire cases for that column is false. So in that case, it is a contradiction. Please, I'll remind you, this particular way of working is not difficult. It's not difficult. You just pick one statement and join with another statement using a particular connective or a connective that you were asked to use. And bearing in mind that each connective has the way it works. For example, if you are using and will only be true if P and Q are both true. If you are using all will always be true, provided there's any true in the two statements. All would only be false if both statements are false. That's it. So please have these conditions with you always. If you know these conditions, there's no way they will put down a truth table that you will not be able to construct. It's as simple as ABC. Okay, let's go to the next page, please. Okay, so before we continue here, I think we are done with the first part of logic. Yes, we are done with the first part of logic, which is what? Which is a propositional logic. We are done with that. We want to go to a predicate logic. Before we continue, please, I want to understand that, or I want to have idea whether the audience are following or not, please. I want someone to type continue, please. I can't continue without hearing from the students or the audience, please. Someone should type continue before I can continue here. We are done with the first part of logic. We want to enter the next part of logic now. Okay, Damila is saying continue. It's okay. All right, so let's enter this particular part, predicate logic and quantifiers. This particular, why I'm saying so is because it makes a whole lot of meaning when you have some attributes of a subject that is common. I repeat, it makes more meaning to apply this part of logic if you have a particular attribute that is common to a whole number of subjects. For example, now, let me say that, okay, let me say Akwa Ibom State has a governor. Okay, let me say, let me say Akwa Ibom State has a governor. Good. Akwa Ibom State has a governor. Okay, I think that's a statement. That's a statement now. That's a statement now. So, so in that particular statement now, let's say you want to leave. I can also say Enugu State has a governor. Now let's leave Enugu State to any state in Nigeria. So you see that all the states in Nigeria has a governor now. So let's say I want to join statement. I want to make a statement about the entire 36 states in Nigeria that they have governor. So will I be governor in the governor till I read all the 36 states? No, it would be cumbersome for nothing. Yes, so there is a way we can quantify that in such a way that whenever you mention a state, you have to just replace the name of state with another state, and the statement keep flowing. So that is why I say this particular state, particular place. I should do what? Okay. Please give me 1 minute. I'll be back now. Just sorry, 30 seconds. I'll be back now, please. Okay, I'm back. I'm back. Sorry about that. Like I said, I have a child here that is disturbing. So we let's continue. Let's continue. So, so what's a predicate? A predicate may be defined as a part of a declarative sentence that describes. For example, now, if I say, Helen is beautiful. Helen is beautiful. So that part is beautiful. It's a predicate. Because what? It's what? It describes the attribute of that particular that particular subject now. Like the one I said earlier now, Akwa Ibom said has a governor. Okay, that thing has a governor, is a predicate. It's a predicate. Okay. So okay, what happened now is let us just do something now that will enable us to see how we can use the same statement, since we have so many subjects having the same attributes in such a way that that same statement can be used for another subject. For example, now let's see how we can have a statement has a governor. Since other state has a governor, we may have a sentence or a statement that will enable any other state to fit into the statement. Whenever I want to. What happened here is we define the predicate has a governor. Let me say we can use something like a statement function. P of X. We can select P of X predicate now. So if you let P of X go, so X with a name of a state, then that particular statement can be made for that particular. For example, now let's say I say okay, let P of X denotes that X is a state that has a governor. So that we use X as a variable now. So that P of X is not really a statement. It's something that is we've never put in. So in that case, you cannot say, okay, X is okay, this statement is true. It can only be a proposition if you place the X with a name of a state. Okay, for example, now if you have if we change, let's say P of X, if you change X, that X to Taraba, for example, now we say P of X to denote that X has a governor. Okay, but if we change the P of X, we now put P of Taraba, P of Enugu. Now we will not be calling it X as a governor, rather we say what? Enugu has a governor. So, please sit down, listen. Okay, so we say that the letter X is called a variable, or you can call it a placeholder. It's just there such that if there's any need to replace it with a subject that will make the sentence meaningful, or that will make the sentence a proposition, you change it. For example, like I said, if you let P of X to denote a statement that X has a state governor. So if you remove that X and write P of Zamfara, the statement will now be what? Zamfara state has a governor. And that is only when you can say that it's a proposition. Okay, so now let's look at what a quantifier is, please. So this takes us what we call quantifier. A quantifier is allow us to talk about the entire subject that is associated with that particular predicate. For example, now let's talk about the issue of let's say a state having a governor. Like we all know that all the states in Nigeria has a governor. Okay, what if you want to say, okay, every state in Nigeria has a governor? How will you put it in terms of provision? How will you put it? Okay, we have a particular quantifier that we call a universal quantifier that enable us to make a statement that relates the attribute to the entire subject. For example, if I want to say all state, every state has a governor, I may say if X is a state in Nigeria, then X has a governor. Please go back to that. Please go back to that quantifier. I'm still explaining something there. Please go back to the previous page. Okay. Okay, so a universal quantifier is a quantifier that makes use of for all. So you will see a sign that is like inverted A, inverted A, inverted A, just like A is inverted. Also, we call that for every or for all, for every or for all. So we call that universal quantifier because it speaks about the entire subject in the universe of discourse. For example, in the case I am saying, every state governor in Nigeria has a governor. Some may say for every X, if X is a state in Nigeria, then X has a governor. For every X, if X is a governor, more meaning because since we know that every state in Nigeria has a governor, then that statement will be true. So a universal quantifier will be true if and only if so a universal quantifier will only be true if and only if every possible cases in the argument is true. For example, if I say for every X, if X is a state in Nigeria, X has a governor. If you want to access this particular thing for truthfulness or falsity, we may try to access the states individually. If there's a single state that does not have a governor, that means the entire statement for every X, if X has a governor, if X is a state in Nigeria, then X has a governor will be false. Or please go down to the next page. The next page. All right, so we have something here to practice now. I want to also look at this particular statement that says that the first says every mango is sweet. The second one says every teacher is generous. The third says every African man is dark in complexion. Okay, the question here is all the duty that we should do now is okay. The activity here is that we should use a universal quantifier and then access the true value of the proposition. Now, the way someone may say, okay, if Please stay on, please. Okay, this particular statement, the first one, someone may say, for every x, if x is a mango, then x is sweet. For every x, remember, this for every, I'm talking about the sign. We're not writing in terms of full. So we just write the inverted A. For every x, if x is a mango, x is sweet. Good. So in that case, that's how we can apply a universal quantifier to that particular statement. For every x, if x is a mango, then x is sweet. The second one, we said every teacher is generous. We can put that like this. For every x, if x is a teacher, then x is generous. For every x, if x is a teacher, then x is generous. Okay. So same thing with the number 3 that says every African man is dark in complexion. You can just say for every x, if x is an African man, then x is what? Then dark in complexion. That's it. Now we look at 4 together now. Let's look at statement 4 together now. Because it's a little bit mathematical anyway, but we want to, because that one is possible for us to just find out the true value of the entire statement now. The statement says P of X. Remember, I talked about what P of X is. It's a statement function. It's a predicate, a statement function. That is not originally a statement. However, what makes it a statement is the value of X. So, because you are using X plus 5 less than 9, what is X in that case? You don't know. So, you cannot say it's a statement, even though it looks like a statement, or even though it looks like proposition. So, what makes a statement is what? The value of that variable. So, if you have a universe of, if you have a domain of discourse, if you have a domain, so you can use that domain to access that particular statement. So this particular one says, sit down. So sit down here now. So this one says is less than 9. And we have been given T to be the domain of discourse. We are giving T to be 1, 2, 3, 4, 5. And the question says determine the truth value of for every x p of x. Very good. Determine the true value of for every x p of x. Now look at how we determine the true value here. We go to the domain or the universe of discourse. We go to the domain that is T and pick those values now, and then put the values in the predicate x plus less than 9. Now, if you access them individually, if after accessing you see that the values are if you so if you put those values and you see that the values are less than 9, then it will be true if all of them are true. Now let's look at the solution here. So we define P1. P1 is when you put the value of this domain 1 into the predicate. Now you see that 1 plus 5 is equal to what? 6. And is 6 less than 9? Yes, it's less than 9. True. Because the predicate said that x plus 5 is less than 9. So for that particular one now is true. Now we now pick 2 again. You see P of 2. P of is when you put the value in, you put P of 2, 2 plus 5 is 7. Is 7 less than 9? Yes, it's less than 9. So that is true. We go to 3. 3 plus 5 is 8. Very good. Is that less than 9? Yeah, that's why you see true. Now, if you go to 4, 4 plus 5 is equal to 9. 9 is not less than 9. Is it true? No, false. Equal to 10 and even more than 9. Is it true? False. Now, because we say for every true, because there's a single F in the entire analysis, we say that the statement for every x p of x is false. I believe that is clear. So that's how we work with the universal quantifier. Universal quantifier says that everything in the domain is true. So if you access based on the values in the domain, and there is any single value that is not in support or that is not true, that means the entire statement is true. Sorry, the entire statement is false. Let me just put another example now. Just come and say every Nigerian senator is corrupt. Let's say someone come and make that statement. Every Nigerian senator is corrupt. Very good now. And that is a statement. It can be argued. Someone can say it's false. Now, okay. Let's say, okay, we want to access this. How do we access this? You can access that without having what? Elements. So you may have to, maybe you want to check those individuals involved. Let's say you have senators now, you just add all their names and start to investigate. So remember, I said someone says what? Every Nigerian senator is corrupt. Someone just made that accusation now. Okay, you want to check now. So what do? You now go to the domain of this course, and now pick the individual involved now and try to investigate. If after investigation you find out that there's one person, or let's say there's at least one person that is not corrupt, that means the entire statement is what? False. That means the entire statement is false. Just like this particular one now, every teacher is generous. Every teacher is generous. Now, okay. Let's say you have names of teachers in a group, which makes up the domain, and now you just check those teachers now, and you find out that there is one that is not generous. That means the statement for every X, if X is a teacher, then X generous is false. Existential quantifier. Next page. Okay, apart from that, there's what we call the existential quantifier. The existential quantifier. The existential quantifier makes use of a sign that exists. It looks like E, but it turns back instead of facing front. Okay. So we have a symbol that looks like E, but it turns to the other way, and we call that there exists, or we call it for some. So we call that the existential quantifier. Now, look at how the existential quantifier works here. Is the one who say that for there exists. Okay, so you will say there exists X such that this particular thing is true. There exists. Okay, if, for example, in the previous statement now, if, for example, in the previous statement, you access now says that there exists X such that X plus 5 is less than 9. There exists X such that X plus 5 is less than 9. In that case, if you find any value of X that satisfy the condition, even though every other ones are false, the entire statement will be true. So for the quantifier that exists, the statement will always be true, provided there is a single value in the domain that makes the statement true. I repeat, in the quantifier that exists, if there is any value in the domain that makes the statement true, the entire statement will be true, irrespective of if every other ones are false. For example, here, the example I say that consider the statement there exists X in there exists X in N P of X, where N is a set of natural numbers, and then P of X is X plus 10 less than 9. Good. So what this is, the domain or the universe of discourse in this case is a set of natural numbers. Is a set of natural numbers. Natural numbers are those numbers like 1, 2, 3, 4, 5, 6, 7, 8 up. See, 1 million and above. Okay. We call that natural numbers from 1, 2, 3 for the natural numbers now. So the statement says there exists a value called x in that set of natural number such that P of x is true. And what is P of x? P of x is what? X plus 10 less than 20. The same way we access the true value for the previous predicate, we apply that same process here by picking numbers individually. And fix in the predicate and calculate of the predicate. That's what we do here. So in this case, like I said, natural numbers are what? 1, 2, 3, 4 up. 1 million arrays now. So if you check here now, x plus 10 less than 20. Anyway, if you pick x as 1, because 1 is a natural number, 1 plus 10 is 11. And 11 is less than 20, right? Yes, true. 11 is less than 20. Very good. And let's also pick something like 5. 5 plus 10 is 15. And 15 is less than 11. Okay, even 5 is true. So P of 5 is true. P of 1 is true. P of 2 is 10. P of 10 is what? 10 plus 10, which is 20, and it's not less than 20. P of 11, P of 12, P of above, after 9, 10, 11, and above makes the statement valid. But because the statement was what? There exists. As long as there is a single value in the domain of discourse that makes the statement true, irrespective of whether there are millions of values there that make the statement false, the entire statement is what? Is adjudged what? True. The entire statement is adjudged true. I believe that is clear. So that is it for the existential quantifier. So even without working this one out, this example of the existential quantifier out, the answer is what? The answer is true. And why is it true? It's true because for the domain, natural number, 1 makes the statement true. Even 2 makes it true. But as long as there is a single value that makes it true, then that statement is true. Okay, please, go to the next page. Okay, we now go to a different thing. We are done with that first part. I think the first part was for logic. I think we are done with logic anyway. This part and up is for linear algebra. This is for linear algebra part. This is the part that we do many calculations. Like I said, the logic part is based on it's just languages. You just look for a way to analyze language, analyze statements for that particular part. So we don't need more of calculator or more of calculation in that aspect. So from this aspect to the end of the class, we will be needing your attention, your ability to add, subtract, do some logical calculation there. Even though you don't have calculator, just try and follow up so that when you try it at home, you get more knowledge about it. Please look together now. We want to start with the permutation here so that I will not be talking for nothing. I want to hear continue. I want to see continue here, please. So that I will be sure that the audience are there listening. If you are here, just say continue. I can see here 10 participants. Okay, I have seen here continue. Please listen, this particular part is very interesting. It's very important, not just interesting, very important. The reason is because combination permutation is used for more and more calculations. I come again. Combination and permutation is very useful. Not because you applied in other topics to find solutions to problems. That's one important thing about permutation and combination. That is why after permutation and combination, you'll be hearing about combination when you get to something like this thing, binomial expansion. Very good. Something like binomial expansion makes use of combination very much. So please pay attention here. Okay, we start permutation now. Permutation means arrangement. a way of arrangement, a way of arranging objects. Yes. So whenever you hear about arrangement, think about permutation. How do you arrange something? Order of arrangement. For example, now, let's say you have 4 individuals in that you want to, you can sit them on that desk. That's arrangement. Show it, and there's an element. So let's start with letter A, B, C. Let me just pick letter A, B, C. As if I'm talking about 3 persons now. 3 persons that you want to sit on a desk or you want to arrange on a desk now. So you may be asking A, B, C as if people you want to sit on a desk now. So arrangement mean what? The order, just twisting it. Okay, this one can sit first, the other one sit at the middle, the other one sit at the other end now. That's after you rearrange, the other one go to the middle, the other one again. Just so how many ways can you twist them till you exhaust the possible way of arrangement? Okay, so let's speak. Let's go with this particular now. So the way of arrange A, B, C can be A, B, C the way it is originally. It can be A, C. It can be C, A, B. You can keep mixing them till you exhaust ways. There is no other way you can arrange them again, and it was not already in existence. Believe you are following the arrangement. You twist it. You pick the one that was at the beginning, put in the middle. Again, you pick that one in the middle, put to the other end, and keep mixing till you exhaust the possible way. If you try that in ABC, you can write that out. You have it now. What if the numbers are A, B, C, D? Let's say there are 4 persons you want to sit on the desk now. In how many ways can you rearrange them till you exhaust the possible way? How many ways? Okay, without writing them down, the way we use, the way you write A, B, C, if you try that, you get 24 ways. Now, just imagine how many and complicated the different persons that you want to be arranged. 4 is 27. 3 was just 6, so 4 27 now. So how many will 7 be? Okay, so because of that, there's a way we work that ways of arrangement out without going through the possible rearranging them physically or practically. So that way is permutation I want to work through now. Okay, that takes us to factorial. We apply factorial in this case first. So let's go through what we mean by factorial. Factorial is an in mathematics that we because and we because of the nature of that particular operation. Baby, I'm doing something, please. I'm sorry. For example, now if I say 3 factorial, what is 3 factorial? Factorial means multiplying that particular value down decreasingly until you reach 1. You multiply it one step decreasingly till you reach 3 factorial is equal to what? 3 times 2 times 1. If I say 5 factorial is what? 5 times 4 times 3 times 2 times 1. So we call that factorial and just multiply them out. And if I say n factorial is what? N multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, up till you reach 1. That's what we call factorial now. Now, let's look at how it applies in permutation. Let's look at how it applies in permutation now. Good. And if you go back to the first example we did, how you can arrange letter A, B, C, and it gives us 6 ways. Let's look at how we can find out the 6 ways, even without arranging them practically. Okay, letter A, B, C has how many letters? It's 3 letters, right? Yes, it's 3 letters. ABC is 3 letters now. So if you pick 3 and attach factorial, if you say 3 factorial, it will give you 6. So instead of doing what? Instead of rearranging them practically, you can just find out the way of rearranging them by saying the total number of the letters factorial. Okay. Now for ABCD is what? 4 letters. If you say 4 factorial, it will give you what? 4 times 3 times 2 times 1. And that will give you 24. So even without rearranging them practically, like I said, you can have the possible way of rearranging them by using what? Factorial. And take notes before you think it goes like that for any other letters. The letters we are working with now, they are all distinct letters. There is no repeating. For example, now if I say, how can you permute confidence? So remember that in confidence, we have some letters that repeat. Now is those letters, those objects that are all distinct. Okay. All right. Now, okay. Based on that, we check through example now. Example, the number of ways we can permute or we can arrange the letters of the word peace is what? 5 factorial, based on what we discussed earlier. Peace has how many numbers? 5. How many letters? 5 letters. 20. 5 times 4 times 3 times 2 times 1 is what? 120. It's very easy to understand. And I give an exercise here. And the exercise is, what is the possible ways of arranging the letter of the word triangle? Triangle. So work that out. Please work that out. The possible ways of permitting the letter of the word triangle. Work that out. If you check triangle, there is no any number that repeats. So in that case, we have no condition attached than to find the permutation of the different distinct letters. Okay? Please, next page. Next page. Okay. Please hold on. Let me do something. Hold on. Watch. Okay. Watch now. You are causing trouble. Okay. Let's look at a different condition of permutation. Because permutation has so many conditions now. Okay. And the question is, what if in the entire object you have that you want to pick some group of numbers and arrange. You want to, for example, now, let's say that you want to do arrangement and you want to arrange them in twos. Let's say there are 5 individuals in the group now, but you want to arrange them and pick 2 at a time. How can you do that? Remember, the other one we just pick all at a time. Yeah, the other one we pick all at a time and work. In this case, let's say there's a condition that says, okay, in how many ways can you arrange 5 individuals in a class, picking 2 at a time? So in that case, there's a condition. It's not like the other one again. Okay. Now, let's check how we can work that. Permuting an object, taking R at a time. We have a formula for it. We call that N permutation R. NPR. N up, then P at the middle, then C as a subscript. So we have N permutation R. So if you've come across a question that says like this, how many ways can 5 individuals be arranged in a class, taking 2 at a time? That means you walk through it using this method we want to explain now. Sit one place. I will sit one place. Okay, so we have a formula for that. And before we explain that formula, yes, I want to just explain how we arrive at that formula now. It's more explanation. Okay, yeah, the formula to obtain that is n function r equals to n factorial all over n minus r factorial. But before we get to that, let me just see if I can explain a little bit about how we obtain that that formula. Okay. Before we get there, let me just tip in this practical example now. Let's say four persons run a race. I mean, four persons run a race now. And you want to find out the number of ways the first and second position can be taken by these four persons. I'm saying you have four persons that run a race now. And you want to find out the number of ways that the first and second position can be taken by these four persons. The answer is 4 times 3. How? Look at how it works here. If four persons run, and you want to pick first and second position now, that first position can be taken by any of the four persons, right? Yes, it can. The first position now can be taken by any of the four persons that's running now. Yes, it can. So you write down or down because that first is important. Now let's I remain the second. So I'm picking the first position. How many persons can pick the second position? Is 3 because one has already picked the first. So 3 remain. So these 3, one of these 3, what? Any of the 3 of them can do what? Any of the 3 of them can pick the second position. So that is why I will come out in what? 4 times 3. 4 times 3. 4 times 3. So if I ask now, take the first, second, and third position. In how many ways can that happen? How many ways? It can happen in how many ways? In how many ways can 5 persons? In how many ways can 5 persons running a race take first, second, and third position? How can that happen? Okay, it can happen in how many ways? 5 times 4 times 3. How? How can that happen? Okay, when they are running, the first position can be taken by what? Any of the 5 individuals. Yes. So write 5 down. Okay, so if someone here has taken any of the 5 are taken the first. Now, how many positions remain now? By the remaining 4 positions now. So if another person has taken the second now, how will remain the 3? The 3 of them can take any of them can take it. That's how we have one. 5 times 3 times 5 times 4 times 3 in that case. So if you apply those techniques, which is very easy to understand if you think through it now. If you apply that, you will see that 4 positions can be taken by 4 candidates in 4 times 3 times 2 times 1 way. So if you multiply this thing out, you will see that if you want to interpret the term of factorial, you will see that at the end you have that the total number permutation, the number of position is equal to the n factorial over n minus r factorial. Okay. So in that case, r equals to n factorial all over n minus r factorial. N permutation r, permuting n objects, taking r at a time. Please go to the next page. Let us have example there. Next page. Okay, examples. Example here says find the value of 8 permutation 3, B 7 permutation 4. Those things are very easy to to find, as long as we already know the meaning of permutation. We use factorial to work this. So once you know the meaning of factorial and how to calculate factorial, it's okay. You see factorial, then you work them out. So if you B, we say 7 all over 7 minus 4 factorial. In this case, n is what? The larger number. So in that case, 7 factorial, all over 7 minus 4 factorial, 7 minus 4 is 30. 7 minus 4 is 30. So you just have 7 factorial over 3 factorial. Factorial is what? 7 times, 6 times, 5 times, 4 times, 3 times, 1 times 2. So if you work that out, you have what? You have X40 as 8 permutation 4. 8 permutation 4. Remember, another way someone can ask that question can be, in how many ways can you arrange 8 individual, okay, sorry, 7 individual in the class, in terms of what? A statement. Yeah, can I decide to put in terms of sentences so that you'll be the one to now say which one is N and which one is R. Please take notes. And once you are able to express them in terms of N and R, you can apply the formula and get the answer as easy as ABC. To a kind of permutation that has another restriction now. What happened to a permutation that occur with a similar object you cannot distinguish? How can you find that permutation? For example, when I make mention of A, B, C, what happened if the word was Aba, whereby you have A and A, those words that are very similar in such a way that even if you twist them, you may not even know where they were kept. Yeah. For example, now, Aba, Aba. How can you rearrange Aba? If you put A, this particular side one time, next time, remember there's another A at the end. When you want to rearrangement now, they are similar. A is very good. So in that case, we have a different way of arranging objects that involve undistinguishable letters. Okay. Okay. If you have such a problem, how can you find the permutation? Okay. This is how you find permutation now. If you have letters, for example, now, if you have letters, for example, like confidence now, so you will now check through letters and count those letters that repeat, those letters that occur twice. Now count them. If letter A occur 3 times, you just put down 3 times. Count B, okay. At the end now, you have so many letters that appear. And then what happens is the number of permutation will be n factorial, ending what the total number of objects, then all over r factorial mean what? Those that repeat. If A repeat 5 times, B repeat 4 times, C repeat 3 times, you will say, okay, n factorial all over 4 factorial times 3 factorial times 5 factorial. Those divisors are what? The number of what? Undistinguishable objects that are repeated. As simple as ABC. So in that case, if X is all over P factorial, P and R those objects that are repeated. Remember, these are not the exhaustive objects. Maybe like 7, 8 objects. Yes, you can just go through them. If there are 7, you can just say P, Q, R, A, C, T. There is 7 objects that repeat. Okay, let's look at example now. Example says, find the number of ways you can permute the letter of the word excellence. Good, that's a typical example now. Excellence. How can you arrange the letter of the word excellence? How can you permute them? Remember, excellence is not like A, B, C, or P's, or triangle, in which there are no repetition in terms of numbers. So excellence here has E is 1, 2, 3, 4. It has 4 E's and has 2 C and 2 L. So before you can do that, if you count those numbers now, the number of permutation will be what? All over times 2 factorial. Both are the divisor part are the repetitions. And once you work them out, you get a number because you are using factorial. Factorial has already been taught in the previous sections. So you can go back to them and look at how you can find factorial. Just below that, you have an exercise which says that you should permit the word Mississippi. Mississippi. And that's simple to do, please. Just check through the other one. Please, if you are listening to me now, I want any of you to work that particular one. This exercise that says that you should permit the word Mississippi. Someone should do that now. Please, I want result in that one. It's very simple. Permit the word, or in how many ways can we arrange the letters of the word Mississippi? Please, I want someone to try that. Let's go next page. Please, after this particular section, we will go to break. After this particular, after combination, we will go to break. Okay, we check the permutation of numbers which may be repeated. All right. So if n different things are taken at a time, in which any item can be repeated without restriction. So the total number of ways is what? N raised to power r. So if you have an item that are repeated now, you just pick the numbers that are repeated, and the number of repeated should be the power to the number of different things. Okay, that is by the way. Let's go to cyclic permutation. This one is very interesting. Yes, it's very interesting because it's very practical. Cyclic permutation is the kind of permutation that arrangement of individual around a kind of arrangement. For example, let's say a meeting that individuals sit around an object and you are asked the number of ways you can arrange them. This is a different case. It's not like the other case. Why? Because in the other case, you were talking about a straight line arrangement that you can start from one end to do the rearrangement. In a circular object, there is no starting point. I repeat, in a circular arrangement, there is no starting point. But the other arrangement, there's a starting point, like say in a desk, we have 2 endpoints. You can start from each of the 2 endpoints to do the arrangement. But in a circular arrangement, everybody is sitting at a in the circle. In that case, there's no starting point. Now, what will happen? You are the one to pick a starting point. So when you pick a starting point, you have removed one person from the group and start from that group. In that case, the number of permutations will be what? Minus 1 factorial. Why is it minus 1 factorial? Because of the one person you remove and start from that place. I believe that is very clear. Yeah. So, for example, now the question says, in how many ways can 6 students? In how many ways can 6 students be seated around a circular table? In how many ways can 6 students be seated around a circular table? Like I said, in that case, since the table is circular, what happens is there is no starting point for arrangement originally. You are the one to fix the starting point. And that place you want to fix the starting point, you have removed one person from the group and start from there. So in that case, the entire number has been reduced by 1. So we have what? N minus 1 factorial. So since there are 6 individuals in the class that I want to arrange, you have removed 1 to start from that particular place. So in that case, the answer is what? 6 minus 1 factorial, which is 5 factorial. If you find 5 factorial, it will give you what? 120. Please try the exercise now. In how many ways can 8 boys? In how many ways can 8 boys be? Okay, in how many ways
can 8 boys form a ring? In how many ways can 8 boys form a ring? Please check that particular exercise. I think that statement is not correct. The 8 boys form a ring. Please check that out. I want someone to just write out the result. It's very easy to find. Someone should write out the result for me. The second exercise just said, in how many ways can 8 different beads be placed in a necklace? In how many ways 8 different beads can be placed in a necklace? It's the same thing. But please, for that particular second part, there's a condition there. There's something else you should think about. Remember, you have to do this particular course has to do with what? Abstract thinking. You need to consider every possibility before you write down a result. So for this particular exercise B, in case you want to try it, yes, it is a cyclic permutation. But again, there's something that's attached. What is attached? Remember, a bead on a neck can be turned. It can be turned. Unlike an individual sitting around a circular object, you cannot turn it upside down. But in a bead, you can turn. It has 2 sides. Both sides can be turned even without noticing. A bead, that round something. You can just carry it and place the other way around. But if it's human being, you cannot carry. So in that case, because of the fact that it can be turned, after finding the normal cyclic permutation n-1, you have to divide by 2 because it can be turned the one way, this side and the other side. That's how you should divide by 2. It's a kind of repetition. Remember. So next page. Next page. Okay, we also have something like a restricted permutation. A restricted permutation, yes. Permutation can be done with restriction now. Okay, let's look at this restriction now. Okay, a condition can be placed or a restriction can be placed in some object. For example, now, someone can say, in how many ways can you arrange people in a meeting in such a way that a husband and wife must stay together? I believe you are listening. So if there's a restriction that you must put husband and wife together, that means you have a restriction. So many restrictions can come into permutation or arrangement. Please listen very carefully. Like I say, you do arrangement. Let's say you are an event manager now. You are thinking about how to put people around when they want to do an entertainment. So maybe you want to arrange this. It's prepared to pick entertainment. So that's the restrictional condition that can be attached when doing arrangement. So this particular concept covers that. Okay. So the normal permutation of any given object taken at a time, in which case particular things never occur, is n minus that k that can never occur with an r. Okay, let's take example first. Let's take the example now. Example says, in how many ways of permutation of 8 things taken at a time will 2 particular things never occur? Very good now. Very good. That in that arrangement, 2 of them will not occur. So you need to put down those 2 numbers that will not occur first and subtract from the total number. Remember, in terms of a husband and wife sitting together now, if you are counting spaces, you need to fix 2 together. 1 space will be removed from that number. Same thing, because the other, that one will not sit alone. He has to sit with the husband. So in this case, it's something occur here. So in the entire thing now, if K will not occur, that means the entire permutation will be what? N minus K permutation R. That is it. So if the entire number was 8, if the entire number was 8, in this case, I already know that you know that 2 will not occur. So the entire thing will be what? 8 permutation 3. I believe you are listening, because of the fact that it was known that 2 will not occur, even though it is there in the group or in the entire number. Since you know that the entire number will not occur, then permutation what? The R. As simple as ABC. Okay, we now go to combination. Let's check combination now. We were talking about permutation and combination. Permutation means what? Arrangement. Remember, in arrangement, the order of placement is very important. In arrangement, the order of placement is very important. But in permutation, you are just selecting. So there's no point for order. That's the difference. That's the clear difference between combination and permutation. In permutation, ABC is different from BAC. In permutation, ABC is different from BAC. But in combination, ABC is BAC. That's just the difference. These three objects. But for permutation, once you change an order, Vision will not recognize that one as the same thing as the previous one. Okay, but for combination, you change order, no need. A combination doesn't respect ordering. Okay, so a combination means what? A number of ways of selecting few objects from the other object. For example, let's say you want to conduct an election in a class. You want to select like class reps in a class of 20. Can I select 2 class from this class? That's it. That's it. So we have a formula for that. Good enough. We have a formula for that. Yes. So we say N combination R. N combination R. N being total number, which must be greater than what? The subset that you want to what? The subset in which you want to select. Okay. All right. Like I said earlier, that order is not important in this case in combinations, and we say N combination R. We write it like NCR, big C, and N is like a superscript at the back. N, okay, sorry, N is like what? Superscript on the at the back. R is what? Subscript. N combination R equals to N factorial, all over N minus R factorial, R factorial. Remember, permutation of what? N factorial over N minus R factorial was combination. But also, sorry, was permutation. But for combination, we attach again R factorial. So the only difference between combination and permutation in terms of that formula is what? The R factorial that is being attached to in combination. Okay. All right. So we say here example, N6 combination 2 equals to 6 factorial all over 6 minus 2 factorial, 2 factorial. 6 factorial all over 6 minus 2 factorial, 2 factorial. Okay, if it were permutation, it would have been 6 factorial all over 6 minus 2 factorial and end there. But because it's combination, we add another 2 factorial. Okay. All right. If you want that, remember I said I don't think I would be spending time to talk about how we calculate, because it is just a process that centers on what? Factorial. It's centered only on factorial, and the concept of factorial was covered previously, and it's very easy, just multiplications repeatedly and reducing one till you arrive at 1. Good, just that. So check that. That is in terms of numbers. Example 1 in terms of numbers. But apart from that, what makes it more meaningful is if you can understand in terms of putting it in language or sentences. For example, we have here, in how many ways can a college 14
11 players be selected of question in terms of sentence, so that a student or an individual has to think through it to understand which one should be N and which one should be R. Okay, remember, N is a total number which you want to select the other one from. So N cannot be less than R. Be careful, so that you will not say 6 combination 12. That is not good. Okay, so in that case, that's in how many ways can college football of 11 players be selected from 16 players? Have what? 11 players. You want to say 11 from 16. So what would be the answer? 16 combination 11. 16 combination 11, which is what? 16 times, as simple as ABC. Okay, so we have an exercise here. Exercise here says, find the number of ways 2 prefects can be selected from a class of 15 students. That was very easy. Please, next slide. Next slide, please. Are you there? Can someone say something? Okay, exercise 2. Exercise 2 says, in how many ways can a committee of 3 ladies and 4 gentlemen be appointed from a meeting consisting of 8 ladies and 7 gentlemen? Please, listen to this particular one now. It's a combination though, but it has 2 sections, 2 different sections. 2 different sections. Because there are 2 classes of people here. So it is also stated that the committee is going to be formed in such a way that they have ladies and 4 gentlemen in the committee. You understand? So in that case, if you want to do combination here, you find out the number of ways of selecting men from men, and again, number of ways of selecting women from women. So you do that in 2 sections. I repeat, because of the nature of this question, which has to do with what? Selecting from 2 classes of individuals, the gentlemen and the ladies, and that the condition is that the committee has to be formed in such a way that at the end they have 3 ladies and 4 gentlemen. So what you should do is, you first of all find a number of ways you should select 4 gentlemen from 7 gentlemen, and also find a number of ways you select 3 gentlemen, sorry, 3 ladies from 8 ladies, and then multiply the 2 outcomes together, and that will be the answer. As simple as ABC. Please try that. Try that. Take note of what I'm saying now, so that when you want to try, you would follow my statement. Okay. We also have restricted combination. Yeah. We also have restricted combinations. There are combinations that also get some restriction. Okay. We have here to find a number of combination of n different things taking R at a time with the following restriction. We pick 2 restrictions. We say P particular thing always occur, and also P particular thing can never occur. Good. Let's look at how we can apply our formula on this condition now. Okay. If P particular things be taken always, thus we have to select R minus P things from N minus P thing. Okay. And again, if P thing can be rejected first, then we have to select R things from the N minus P thing. Okay, we would find that out in an example. Example here says, for a company of 15 men, how many selection of 9 men can be made so as to exclude 3 particular men? Very good. Okay, you want to select 9 men. from 15 men in such a way that there are 3 main individuals you don't want to put. Yeah, for some individual that do meeting before meeting, let's say they want to do selection before that they have gone to their meeting and state some name they don't want to find the committee, so that whatever policy they are playing in the selection, these people should not be there. Even though you are there, you think they will select you, they have already excluded your name from the meeting. This is what they do. Yeah. So if at all they have an individual that they don't want to put in the meeting, the thing is that the entire number that they want to form has been put on restriction now. Yes, there's a restriction on that because of the 3 individuals that they want to. Okay, removing the 3 particular names in this case, we have to select 9. There has been what? A deduction, a restriction on the total number because of what? The individual that must not be in the group, that must not be in the group. So even though the entire people that seated there thinks they will be in the group, because of the condition that this individual will not be in the group, it's just a total number for nothing. This individual has to be removed because they don't cause any possibility of selection in the group. So that's why they can be selected. So the result now should be what? 15 minus the 3 individuals that are excluded, all by number that they wanted to select. So that's it. So that means that we have 15 minus 3, those men that were not to be selected, combination what? 9 individuals they want to select. So the answer becomes 12 combination 9. 12 combination 9. Please go and find that out. Okay, next page. We are done with the restricted combination. Next page, let me see. Next page. Is it my network or what? Yes. Yeah. Good enough. I so much like this. I didn't even check that there were numbers coming in. Okay. All right. Okay. 8 minus 1 factorial. Very good. Very good. Okay, this 8 minus 1 factorial. Who is this person? Oni Ife Very good. In Ife if this 8 minus 1 factorial is the one that I said bit, remember that I said since the bit, something that can be turned to the other side. Remember, bit has 2 sides now. This other side can be 1, and the other side can be 1. So in that case, since it can be turned, you have to divide by 2. I'm saying if it is that bit. So whenever you are doing anything, understand that the other side, you need to divide it by 2. Yes, that's it. Thank you very much for the responses. Yeah, it makes me understand that the people are following. Thank you. God bless you. Okay, next page, please. Hello. Is it my network or what? Okay, right. Oh, okay. I think I think break. I think this should be break time, please, because we will start. I think we'll start from binomial expansion in the next section, and let us have some break. Hello. Can the host say something? Can the host say something? Someone should say something because I'm thinking we should go for break. Or can I continue? If I'm to continue, please, I should continue. I will continue if, okay, should continue. That's okay. That's okay. I'll continue. Okay. All right. We have exercises here anyway. A student is to answer 8 out of 10 questions on an examination. How many choice does he has? It's okay. That's a combination. To those of you that are in school, when they say that, when they give 7 questions and ask you to answer 5 questions, so you can just think about how the choices you have by doing combination because you are selecting. Good. So this question is a typical example of the question we answer in our exam hall, that we have allowances in terms of the number of questions that is being asked and the number of questions that we are expected to answer. And so those are the possible things you can think through it. Like, because this was okay, a student is asked to answer 8 questions out of 10 questions on examination. The question here is how many choices has he? Okay. The second question is how many choices are there if he must answer the first 3 questions. Try that exercise. Maybe in our next class we should. I think I would demand the answers to this question, please. So question 2 says, out of 16 men, in how many ways a group of 7 men may be selected so that particular 4 men will not come? Particular 4 men will always come. Good. Those are all restrictions. Remember, we've solved something like this before. The one I said that in a meeting, before they even have the meeting, they have already mentioned names that they don't want to be there. So even though you are there in the group that they want to select, you have in your head, they will not select you. So you are not a threat to anybody. You are not a threat. You don't form any option. Any name that has been marked down that must not be selected, do not form any option of selection. So in that case, it's just like they are not there in the number. Those ones that have been try these particular exercises. Try the exercises now and respect the conditions. Okay. Now let's go to binomial expression. Binomial expansion. Okay. A binomial expression is an expression of the form, let's say x plus y to the power n. In short, whenever you have 2 groups of objects in a bracket, whenever you have 2 groups of objects in a bracket raised to a certain number, that expression is called a binomial expression. We face this kind of expression in schools. So many schools, we have to face this kind of expression whereby you have to expand. Those of you that can remember expansion, expand. You don't even think about which kind of expansion. You are expanding something binomially. Because sharing a common power is called what? A binomial expression now. Even if there are not 2 elements, remember, because when I say 2 elements, it doesn't mean that if there are 3, there are ways you can bracket part of them so that they form what? 2 elements. Yes, you can force them to become 2 elements, sharing a common power, if there are more than 2 elements. Okay, so we call that what? Binomial expression. Now, what is binomial expansion? Binomial expansion is a way or a theory or a method that enables us to expand this particular object. Expansion of binomial expression can be difficult and tedious without a proper technique. It can be so tedious. For example, now let's say the normal expansion that we have a bracket and say x plus y multiplied by x plus y. You just, okay, let's say x plus y squared. Because there are 2, you multiply them together and start to multiply them. Good. That's the method. If they say x plus y to the power 3, you try to multiply in terms of 3. Why do you say x plus y to the power 20? Will we be able to do that? So it can be tedious without the application of a proper theorem. So a stable theorem that enables us to expand that what we call what? Binomial theorem. Binomial theorem. Binomial theorem. I made it clear earlier that combination is being applied for binomial expansion. When we were doing that, I said that combination is very important, not because of the way it is, but it's because even as you run the course, you will see that they are being applied immediately. So if you have understood combination, that means this particular part you should be able to flow. That is why in every school, before anything binomial expansion, they must first of all touch this thing. They must touch a combination because it's the idea of combination that's being used for binomial expansion. Okay, so let's go to the binomial theorem properly. It's a long theorem anyway, but it's something that is very easy to understand because it's just combination. Okay, so binomial theorem can be classified. We can classify binomial theorem into two parts. The part that has to do with positive integer, like the integer power, and the part that has to do with non-integer power. And in that case, we can score that one a general case because that particular part can also be applied in this integer part. But let's start with what? Binomial for positive integer. Okay, let's say that we have two elements called A and B in a bracket. B is operated B by plus raised to power n. And I want to expand that. N can be any number. And let's, in this case, we assume that n is a positive integer. So we have that the expansion of that will give you x to power n plus n combination 1. One thing. When I was doing combination, I think I used C alone. I used C. There is another way we write combination. There's another way we write combination. We just form a bracket, a tall bracket, and put n and x, n up, x down. So we say n combination x instead of using C. So if you don't want to use C, you can use this. Both of them are the same. So please bear with me that just understand that I'm talking about combination here. Sorry, I did not mention that. So this is the sign we use as combination here. So if you have expand the expression x plus y to the power n, we say it's equal to x to the power n plus n combination 1, x to the power n minus 1 multiplied by a plus all of that. Let me just help them so that they understand properly. Think about a binomial expansion in let's say in a way that, let's say you want to, in a way that you want them. Let's say you want to share a particular number of items to two individuals. Okay, let me just be precise now. Let me say that item is 5. Let me say that item is 5 now. You want to share it to individual. The individual I'm talking about is A and B that is in bracket now. I think these are the possible sharing. The first person can take the entire 5 objects, and the other one takes 0. Yes, it's possible. It's possible. They can give you 5. They can give 5 items in 5 items to be shared among 2 people, but one person will carry all and didn't give the other person. It's possible. It's possible. Okay, that is a case that you have x to the power n. X to the power n is a case that the first of the x takes the entire n objects, and the other one do not take any. That's why you do not see the other one in that first n, because anything to the power 0 is not 1. So 1 multiplied by x to the power n is x to the power n. So that is it. So that's why you have that first term. What? Next term now. Another way of showing is the first person can take 4 instead of 5 and give the other person 1. 4 is what? 4 is n minus 1. 5 minus 1. That is why you see here, this one is what? X to the power n minus 1. The other one is x. You don't have any power. And now, why do we have x combination 1? In how many ways can you share the entire 5 objects? the possible way of showing the five, go here. Go down there. Oh, sorry. Okay, so the same thing. So as you keep going, if you go to the next term, you will see. Okay, you see. Okay, you see the if you go to the next term, you can say, hey, what happened? Why is it 3? 3 minus 2. So the remaining is given to the next person. That is why you see anything that's being subtracted is given to the next person. That's what you call it binomial expansion. So whichever thing that is remained from this person is given to the next person. So please go back. Just go back. There's something I'm explaining. Okay. So we call this binomial theorem now. We were using combination in that first part. So that equals to x power, and we have been able to translate it into factorial terms. Remember that in combination we do factorial. So first line combination or the second line that is the combination, so that those that will not like to work through combination can work through factorial straight. Okay, go down, please. Go down. Next slide. Okay, example. Let's pick example now. Example says find the first 5 terms in ascending power of x of this. What happened is you are asked to expand that expansion. You have to expand that of that expansion now, and the condition is that it should be in ascending power of x. Okay, if you see the solution, we just apply the formula. We just apply the formula. For example, the first term is a in the bracket, and the second one is 3x. So in the first thing now, 2 pick the entire 7, 3x pick 0. That's why 2 to the power 7 is the first thing. The next term is what? 7 combination 1. Because 1 has been transferred 7 objects to one person. Okay, so it's taking one at a time. Okay, so if you apply that thing, if you work those combinations using the method you learned earlier, it will result at 28 plus 134x plus all of that. All right, so from expansion now, deduce. The first feature is that expansion has 8 terms, although we will only ask to write down the first 5 terms. And again, in each of the terms, the power of 2 sorry, each of the terms, the power of 2, the power of 2 and 3x sums up to 7. What happens is, if you are doing expansion, the power of the 2 variable, the power of the 2 elements must sum up to the power of the entire bracket. Yeah, that is so the power of the 2 then must sum up to the power of the entire was decreasing. The power of x was increasing. Please go down. Okay, before we move down, expansion of a plus 2x raised to the power 5. You see, maybe by next slide, if you look at it. Try this. It's not difficult anyway. It's very easy to do. Just try to share A and B. A to the power 5. then 2b to power 0. The next term to be what? 8 to power 4, then 2b to power 1. The next term to be what? 8 to power 3, then 2b to power 2. That is it. As power of A increases, power of B decreases. That is it. So the first term should not have any combination. The second term should have 5 combination 1. Next time you have 5 combination 2. The next time you have 5 combination 3. Till you go and reach 5 combination 5. It's very easy. Okay, go down to the next page. Next page, please. Please, I want someone to tell me. Someone was here saying, let's go break, please. Which one are we? Which one are we taking? Is it break or we should continue? But I will prefer to continue so that I can end on time. My baby here is disturbing too much. So, but which one do we go with? Is it continue or break? Please let me hear. Okay, we now go to binomial expansion for numbers. This is like a general case. Please expand it. This is like a general case, which can also work for. It can also work for integer power or integer index. Okay. Now in this case we have a formula 1 plus. We have 1 plus x to the power n. Which equal to 1 plus. Anyway, before, let me explain why we have this formula now. Remember that in the other one for integer power, we use combination. But in this case, we refuse to use combination. We use only n minus 1. Why do we do this? Good. See the reason here. Remember that combination is only defined for positive values, not negative and not fraction. That is why you hear 5 combination 4, 5 combination 3. In how many ways can persons you do not apply permutation? You want to expand, and the power of expansion is negative. There's no way you will apply a binomial formula that has to do with what? Combination, because combination doesn't work with what? Fractions and negative. So that is the extent that this particular formula emerged. It emerged and enabled us to work with what? Fractional power and also negative power. Okay, for example, now look at this. Expansion that says that you should find that you should expand the following term. Okay, that you should expand the following to the term containing x to the power 4. The first one says 1 over this. Second one says 1 over this. Okay, if you look at those binomial expressions, their powers are negative or fraction. They are negative or fraction. For example, now, let's say we want to work the example A. You will see that if you put the example A properly, we have that the expression becomes 2 plus x raised to the power minus 3. So the power is negative in this case. And in that case, there's no way you can work with the formula that contains combination, because negative value doesn't work or doesn't function with combination. Okay. All right. So if you apply that formula anyway, if you apply that general formula anyway, that says that. If you apply that formula that says that 1 plus x to the power n equals to 1 plus nx then plus n into n minus 1 all by 2 multiply 1 up to that, the terms are still going. So if you want to apply that, which is the one you must apply in this case because of the power is negative. So look up the formula. I will work for, let's say, first two terms here. Okay. the first thing we do here is to express the entire thing in such a way that the first term is 1. The first term in the bracket, and the second term can be anything. So we have been able to express that to become 1 plus x over 2 raised to the power minus 3 now. So following the formula, you say the first term is 1. So we just write down 1 as the formula. We write down 1 from the formula. So the next term is nx, n multiplied by x. So you check this expansion, and that's why you will see after 1, you have plus bracket negative 3 multiplied by x over 2. Okay, let me go to the next term. The next term says plus n into n minus 1. Okay, n is 1 in this case, minus 3. N minus 1 in this case, minus 3 minus 1 is minus 4. Okay, that's why you see the minus 3 multiplied by minus 4 multiplied by x raised to the power 2. So please, you follow that same technique. Just respect the operation of the formula. Then at the end, you will work it, you will have it. All right, so we look at the properties of this binomial coefficient. Okay, we didn't explain the meaning of binomial coefficients. All these combination, in short, whenever you see combination in the binomial expression, those things are trying to give you the coefficients of the variable. So we call them binomial coefficients. Those values that are attached to variable x squared, x something, okay, those values. And we get them mostly from combination of what we call Pascal's triangle. I sorry, we don't treat Pascal triangle here. So we have all coefficients in x plus a n for binomial expansion is n plus 1. Now what happens is if you have, for example, now if you have to expand, for example, x plus y raised to the power 5, after expansion fully, the number of terms you will have will be 1 greater than the power. That's why we say the number of terms for binomial expression is what? N plus 1. Yeah. Again, that the first term of the expansion is 8 power n. The first term is always what? The first thing raised to all the power, because if you are sharing it, like I said, one person may take all the power and the other one is not shared to anything. So the other one will take 0. And in that case, anything that is to power 0 would escape because only one will be left. Okay. So that is why the first term is always what? 8 power 1, while giving the other okay, let's go to the next page, please. I think there's nothing more to talk about. Next page. Next page. Okay. Well, let's go to where I will apply this binomial theorem. Yeah, binomial theorem can be applied in approximation. Yeah, we apply them to approximate some expansion. Yeah. Don't make noise. We are listening. We don't make noise. You go now. Don't make noise. Take. Okay. Example here says that we should obtain the expansion of 2 plus x raised to the power 4 and use the result to find the value of 1.99 raised to the power 4 and connect to 4 decimal places. Okay, it's okay now. Go there and play. Go there and play. Don't disturb. Okay, so if you have to do that now, I want to bring out one thing now. If you see the value 1.94 to the power 4, 1.94 to the power 4, you will see that you can express that 1.99 to the power 4 in terms of 2 plus x to the power 4. For example, now 1.99, it can be expressed as 2 minus 0.01. Try that, you will see that 2 minus 0.01 is what? 1.994. If you express in terms of 2 minus 0.01 to the power 4, that means you have been able to bring it close to 2 plus x to the power 4. Because we have here the first term is 2. And the second term is x. And here the first term is 2. Second term is minus 0.01. So what you should do there is to find the value of x that equals minus 0.01. That is it. Now, before you do that, we first of all what? Expand 2 plus 4 to power x using the binomial theorem. If you expand that, you have this up to 2 plus x is very easy to 2 plus x to power 4. You have only small power. So you can easily expand that. Good. So if you expand 2 plus x to power 4, you have the result to be what? 16 plus 32x plus 24x squared plus 8x to power 3 plus x to power 4. Now, after having the result like that, the next thing to do is to express, like I said, 1.99 to the power 4 in terms of 2 plus x to the power 5. If you do that, you have that 1.99 is what? 2 minus 0.01 to the power 4. Yeah. So if you look at 1 if you look at 2 minus 0.01 to the power 4 and 2 plus x to the power 4, they are almost the same. They have same power. And they also have same base term in the bracket. So the only difference is what? X, and good enough, X is a variable. X is a variable 0.01. So you find that you see that X is what? Minus 0.01. Very good. If the first term you have 2 plus x to the power 4, and the second term you have 2 minus 0.01 to the power 4. That means X is what? Minus 0.01. That is it. Now, what you do and replace whenever you see x with what? Minus 0.01. That is what we call approximation. So if you replace x with minus 0.01 in the expansion of 2 plus x to the power 4, and sum everything up, you have power 4. And that's what is been done here. As simple as that. So the first thing, expand it using binomial principle. Expand it. The second thing, you do is express plus x to the power 4. And now the second bracket. And find the value of x that equals to, that will make the first bracket equal to the second bracket. Once you find that, you place the value of x in the expansion of 2 plus x to the power 4, and then add it up. You have the final answer to be at approximate value of what? The expansion of 1.99 raised to the power 4. Please, next page. Next page.
For my next page.
Yes.
Uma, are you there?
Go there and there. So the application of binomial theorem is mostly for expansion of some compared with the expansion of a binomial expression containing a variable, and then compare the two brackets and find the value of x that equates the second bracket. From there, you can replace the expansion with that value and work it out to have the value of the expansion. Please, I want you to go to the next page so that we can. Next page. Okay, we are now in matrix. That means this is our last part, although matrix is also large. This is the last part, and it's very interesting. And before we proceed, please, if you're having any issue, you can even if you ask today or some other day, we can explain it. Yeah, just try to get your question. Yeah, we can work it out and also try to do some whether a video or whatever will help you to understand the steps you go through to solving the question. Please try and ensure that you understand what we do. It's not just doing for doing sake, it's for you to understand. And one thing I don't like doing is talking for nothing. Whether we still have people listening before I progress, even though I am aware that it's being recorded so that any student can get the clip some other day. I still want people to follow because I can't just stay like this and do video for nothing or do some clip for nothing, please. If you can understand now, you can ask question now or you can ask question later. Yeah, we can still put you through. This thing is not difficult. It's something that you can do it, but if you do not sit down or if you are not ready to study, you still don't know it. Just ensure you go through it and ask questions when necessary. Okay, let's go to matrix operation and determinant matrix. Maybe you are disturbing people. You are disturbing activity. Go and sit down there. Go down here. Sit now. Sit. Okay. A matrix is just a rectangular array that arrange values or elements in terms of column and row. A matrix is a rectangular array with arrangement of values in rows and column basis. Okay, in calling a matrix, you call the row first. Please listen. When you want to talk about matrix or you want to call the order of a matrix, you mention the row first. We say a matrix m by n. A matrix is of order m by n. M is what in that case? The row. N represent what? The column. So if I say that I have a 3x4 matrix, what I mean is that the matrix I'm talking about has what? 3 rows and 4 columns. Okay, so look at the matrix like this. A matrix is like a rectangle, let me say like a rectangle that has elements inside. So if you look at a matrix like this, to the left, the left side, the part of the left side. Now we call that part the rows, the row. Those left side are the row. Now the part that has to be what? Up down. If you look at the up line, we call that the column. For example, if you okay, I think go to right. For example, we have the types of matrices. We have the types of matrices now. The what we call the row matrix and the column matrix. Want to write? Go down. Sit down there. Okay, sorry. And we have a type of matrix here, or special type of matrix here. Okay, we have what we call the row and column matrix. The row and column matrix. Any matrix that has only one row, we call it a row matrix. Whereas any matrix that has only one column, we call it column matrix. A matrix with one column is called, okay, the first example we have here, a matrix containing only one column is called column matrix. Now, look at this matrix example is PQR. PQR. You see, a column is the one that stands like this. A column is the one that stands like this. For example, now, in the first matrix we have here, A, you will see A11. You will see A11, A12 up to A1N. A11, A12 up to A1N. The A11 that I'm reading from left to right. From left to right is the row. The one I'm reading from up down is the column. That's why we say column matrix. It means that has only one column. PQR is reading what? From up down. PQR up down. So that is the column. Okay, compare that to a row matrix, which has only one row. Example here, PQR. Look at the way you write the PQR from left to right. Okay, so we call that the, please expand it. Okay, after that, there's something we call square matrix. A square matrix is a matrix that has same number of row and column. Row. We call it a square matrix. For example, now we have example square matrix here. A 3 by 3 matrix. It has the number of rows is 3 and the number of columns is 3, making it a square matrix. Another example can be a 2 by 2, a 4 by 4, a 5 by 5. So whenever you have an M by M or an N by N, we call that what? A square matrix. We call it a square matrix. Okay. There's another one we call a diagonal matrix. Only non-zero elements in the main diagonal. A main diagonal is the central line in a matrix, in a square matrix. If you have played draft before, you will see a central line that takes from one end to the other end. We call that the principal diagonal, or we call it the diagonal element. So a diagonal matrix is a kind of matrix which the only non-zero elements are found in the principal diagonal. Okay, so an example matrix is what I'm writing here. Remember, in a matrix, you can have in terms of letters. It doesn't matter as long as you have. Okay, and what I did not mention, we always use the capital letter to denote a matrix. That's why you hear a matrix A, matrix B, matrix C, matrix Y. So we use capital letters to name the matrix. And also we can use small letters inside the matrix. Yes, we use small letters to denote what the elements in the matrix. So those numbers you find inside the matrix are called the elements of the matrix. So the entries in the matrix are called what? The elements of the matrix. Okay. All right. So another thing I may like to talk about now, which is very important, is how to locate a value in a matrix. How to locate go back. How to locate or how to pick or how to identify a value in a matrix. For example, now, okay, we are here at the scalar matrix. Scalar matrix now. A scalar matrix is also a diagonal matrix. A scalar matrix is like a diagonal matrix, but for scalar matrix, the diagonal elements are equal. So if you have diagonal elements are the same, we call that what? A scalar matrix. For example, now look at this one now. Even though its entries are only four, making it a scalar matrix. Apart from that, we have what we call the norm matrix. So if you have all the entries in the matrix to be 0, we call that norm matrix. The other one we call triangular matrix. Triangular matrix is divided into 2: the upper triangular and the lower triangular matrix. Now, what makes the triangular matrix is that one part before the main diagonal are all 0. For example, now for upper triangular matrix, all the values below the main diagonals are all 0. Yeah. Another thing we have another thing we call the identity matrix. Identity matrix is a diagonal matrix in which the principal diagonal elements are all 1. So we call that unit matrix or identity matrix. Okay, go down. Next page. Okay, we now come to the section of operations on matrix. Addition and subtraction. This is very important. How we can add and subtract matrix, and how we can multiply. And okay, we don't divide matrix, we can multiply. So let's look at how we add and subtract matrix first. Okay, if you want to add or subtract matrices, let's say you have 2 or 3 matrices. First, the matrix must be of the same order. You cannot add a 2 by 2 matrix to a 2 by 3 matrix. It will not work. Only add a 2 by 3 matrix to a 2 by 3 matrix. You can only add a 2 by 2 to a 2 by 2. So before a matrix or matrix can be addable, they must first of all do what? Be of the same order. That's the condition. Apart from that, they will not add. Now, if you want to add them, what do? You add the corresponding element. You add the corresponding element of both matrices together, just like normal addition. However, you pick an element even though you want to subtract, you subtract that. Subtract what? The corresponding element. And add what? The corresponding element. Scalar. Scalar. But when you arrange them in a row, we call that vector. A single part is what we call scalar, like 100, 5, 10, we call them scalar. But if you arrange them in a row, let's say a row that contains ABC, we call that a vector, whether a column vector or a row vector. However, if you now arrange them in row and column, we call them matrix. Just how values are arranged. But what happens if you want to multiply a matrix by a scalar? For example, now let's say scalar is 3. I want to multiply the scalar by the entire matrix. What you do is you multiply that scalar by every element in the matrix. If the matrix is 3 by 3, I want to multiply that 3 by 3 matrix by a scalar 5. What you do is you multiply everything in the square bracket by that 3. And the result is the multiplication between the scalar and the matrix. Okay, so based on the explanation, we want to look at those examples below now. For the following matrices and scalar, evaluate. So the first is you should add matrix A plus B. The second is you should subtract matrix B from A. And the third is you should multiply the scalar C by A. You see here we have matrix A, matrix B, and the scalar is 3. Okay. So if you look at the first one, A plus B, you will see that we have put down the elements, the matrix A and plus the matrix B here, and equals to, if you look at the first element in the result, you will see that the first element is 6. How is it 6? 5 plus 1 equals to 6. Please check that. We pick 5 because it's the first element of the first matrix, and add to 1 because it's the first element of the second matrix and equals to 5. Again, the next is 5. The next in that particular row is 5. Why is it 5? Because we pick the next element in matrix A and add to the next element in matrix B, which is 2, and that gives us 5. Every other element in the matrix are added similar in a similar way by picking the corresponding element and add it to the other one. For example, the last element in the result is 6. Why is it 6? Because the last element in matrix A, which is 0, is added to the last element in matrix B, which is 6, and 0 plus 6 is what? 6. That's it. That's how we add. For subtraction, we do the same. We subtract the A11 being subtracted from, subtract B11 from A11. Subtract B12 from A12. That's what we do. For example, now, for A minus B, you will see the result here is 4. The first result of it here is 4. Why is it 4? Because 5 is the first element of matrix A, and 1 is the first element of matrix B. 5 minus 1 is 4. The last element is minus 6. Why is it minus 6? Because the last element, which is 0, in matrix A, okay, and the last element is matrix B is 6. So 0 minus 6 is 1, minus 6. That is it. That's how we do. So you can as well find 3A. How can you find 3A? 3A is what? Multiply 3 by matrix A. That's what we do here. So if you say 3 multiplied by A is what you should do what? It should be 3 multiplied by 5, 3 multiplied by 3, 3 multiplied by 1. And that's how you have 15, 9, 3, minus 6, 12, and 0. Because you multiply everything there by the scalar. Okay, next page. Next page, okay. All right, we have here matrix multiplication. How do we multiply two matrices? Remember, the other one we're only talking about scalar and a matrix. This one we want to talk about what? Two matrices being multiplied together. Even if you want to multiply 3, 4, 5 matrices, you will multiply them one after the other. If you have 3 matrices to multiply, what you do is multiply 2 first. Take the result, multiply by the next matrix. Take that result, multiply by the other matrix till you finish all of them. You can do that with addition. If you have like 4 or 5 matrices to add. If you are not the kind of person that will be able to add and subtract at the same time, all of them, what you should do is pick 2, add. After having the result, pick the other one, add with the result. That's how you add till you finish. For multiplication, I wouldn't even advise you to add to multiply it at the same time. You will not work. Multiply 2 first and take that result, multiply by the next one. Okay, let's see how we multiply. Multiplication of matrix is a little bit complicated. It's not like addition. The way we operate it, there's a particular way we operate it. We operate like this. We pick the row of the first matrix and multiply by the column of the second matrix. I repeat, if you want to multiply 2 matrices, let's say A and B, what you do is pick the row of the first matrix and multiply by the column of the second matrix. That is why before 2 matrices can be multiplied together, the order must agree. How would the order agree? The order will agree if the number of rows in the first column equals, if the number of rows in the first matrix equals the number of columns in the second matrix. Apart from that, it will not work. A matrix can be multiplied, 2 matrices can be multiplied if the number of rows of the first column is the same as the number of columns of the second matrix. That is the only way you will multiply them. Now let's check as we go. Okay, let's say that we want to multiply. Okay, the question here says we should do what? We should multiply AA. A is like say A squared. And we should also multiply AB. And we should multiply CA. Okay, let's start with, I think if you know AA, we can apply the same knowledge with the AB. So how do you multiply AA? We write down the two matrices AA together. So we put down A and also put down A again because A squared. Now we pick, remember, both of them are 2 by 2. So we pick the row of the first matrix and multiply by the column of the second matrix. How do you multiply? So we pick, the thing is 1 times 1 plus 2 times minus 1. The first row is what? The first row of the first matrix is 1, 2. The first column of the second matrix is what? 1 minus 1. So we pick 1, 2 and multiply by 1 minus 1. How do you do that? You say, okay, 1 times 1 is 1. 1 times, 2 times minus 1 is minus 2. That is why you have, at the result, 1 minus 2 first. After that, you pick that same first row and multiply by the second column. That same first row, you multiply by the second column. It will be 1 times 2 and the answer is 2. And 2 times 0, the answer is 0. That's how you have 2 plus 0. Again, you move down to the second row of that same first matrix. Second row is what? -1 and 0. And then you pick that and multiply by the first column again of the second matrix. And you also multiply that with the second column too. So you have here -1 and 0 multiplied by -1 and -1. 1 and -1. So -1 times 1 is -1. That's why you have at the second row of the result, you have -1. And you also again pick 0 times -1, which is 0. So that's why you have the -1 plus 0. And again, we pick that same second row of the first matrix and multiply by second column of the second matrix. So -2 times, -1 times 2 is -2. Then you have your -2 plus 0. Okay, that's how you have the -2 plus 0. So after that, you add up the entire thing you have in the bracket. So why we have -1 is, we say 1 minus 2 is -1. I will have the 2 plus 0 is 2. -1 plus 0 is -1. And -2 plus 0 is -2. So that's how we multiply. We apply that same multiplication tactics. We apply that the same multiplication skill to every other multiplication. Even if they are 3 by 3, 4 by 4, you don't have any issue. If at all you apply that same technique. Okay, we have exercise. The exercise says that you should, okay, see above. Okay, you should multiply CA. Since you have been able, you have done already, you have done AA and AB. You should try and multiply CA. Use that same technique. Please go down. Let's go to another page. Go to the next page. Okay, we have now transpose of a matrix. Transpose is just a rearrangement of a matrix in such a way that the column element will now become the row element, and the row elements will go to the column, become the column element. I repeat, a transpose is a rearrangement of a matrix in such a way that the row elements are taken to the column side, and the column elements become the row elements. That is it. And we do not transpose by T. So transpose is, if you want to transpose matrix A, the command will be that they will write A raised to power capital T. Some use small t, some use a kind of apostrophe, meaning transpose. So I like using T. So if I give, remember I said that we use capital letters to denote the matrix, something like A, B, C, Z, those capital letters. So if I say let the matrix A be this, and I say obtain A raised to power T, that means I obtain what? Transpose of matrix A. I am asking you to rearrange. It's very easy to rearrange. What do you do? Just that row, pick the second row. Okay, what I mean is, for example, now we have that example. If A equals to 1, 2, 3, 4, 5, 6, then A transpose is what? You see, okay, the row elements were 1, 2, 3. Now it becomes the column elements 1, 2, 3. You see, the column elements were 1 and 4. It now appear at the row of the transpose. You see, so 80 now become 1, 2, 2, 5. Okay, sorry, 1, 4, 2, 5, 3, 6. Instead of 1, 2, 3, 4, 5, 6. I believe that is very simple to do. Again, we have here example 2 that says consider the matrix B equals to this. Then B transpose is okay. B transpose is like this. Okay, 0, 0, 2, 3. Okay, so the B transpose is, we had this thing, row elements to be 0. The first row elements to be 0, -1, and 3. I'm talking about the matrix B. The first row elements were what? 0, -3, and 2. 0, -3, and 2. If you look at the transpose matrix, you will see that they now become the first column elements. The first column element now becomes 0, -3, and 2 instead of 0. Instead of the previous 0, 3, and -2. You see? Now, let's look at the second row element of the previous matrix, which was 305. Is now a different thing that appeared in the transpose matrix. Instead, the second column element become what? 305. So that's how transpose are being done. You pick the row element in the matrix and make it become column elements in the transpose matrix. That's how it is done. Okay, and there's a size here that says if a matrix Q is given by this, that you find the Q transpose. That thing is very, very easy to obtain. Let's move to something else now, which is minor cofactor and determinant. A minor anyway, you will find minor anyway. A minor is just a determinant of a submatrix. A submatrix. If you have like a 3 by 3 matrix now, and you want to find a minor of that matrix, you have to break down that matrix into 2 by 2 matrices. There's a way of doing that. Okay, we will get to that. Now, a determinant is what? A determinant is just a value we obtain. It's a special value we calculate from the matrix. We call it determinant. It's a special value we calculate from matrix. And we have a method of working through determinant and the rest. All right, so let us look at how we can evaluate determinant now first before we go to the minor and the cofactor. We get cofactor from minor. Once you have a minor, the minor, that means cofactor is very easy to understand to get. Okay, so let's start with the determinant. Like I said, determinant is just a special value you calculate from a matrix. And determinant is very useful in terms of matrix inverse. If you want to calculate the inverse of matrix, you must calculate determinant. You must calculate determinant. Okay. Now, so how do we determine the determinant of a matrix? Okay, let's start with a 2 by 2 matrix first. If you have a 2 by 2 matrix and you want to obtain determinant of a 2 by 2 matrix, what you do is to look at the principal diagonal element of the 2 by 2 matrix and multiply them, and then subtract by the right hand side diagonal element. For example, now, please go back, please go up first. There's something I'm explaining. Okay, let me explain this first. For example, now, if A is A, B, C, D, now the principal diagonal element is AD. So the determinant of A should be what? AD multiply AD, then minus BC. BC is the other diagonal element, but you subtract from AD. Again, but if you have 3 by 3 matrix and you want to find determinant, one of the ways is for you to break down the 3 by 3 matrix into 2 by 2 matrices. For example, you see here for 3 by 3 matrix A, B, C, D, F, G, H, I. We have broken them. Now, how do you break them down? You pick the first row element. Once you pick the first row, you cross out the row element and the column elements associated with that particular value you pick, and then write down the remaining elements. That is it. So go to the next. Go to the next. Next page. Next page, please. Yeah. So here we say that we should find the determinant of matrix A. Good. And we want to find it with the first method. The first method is to do what? To break down the matrix into 2 by 2 matrices. Remember that the determinant of the 2 by 2 matrix is very easy to find. Just multiply the diagonal element and multiply the other diagonal element and subtract them. That is the way out. But for 3 by matrix. There is no way you can do that. And approaches is to do what? Break down the matrix into what? 2 by 2 matrices. And how do you do that? Look at how we do it here. We pick the first row. We just pick each element of the first row. There are 3 elements in the first row, 1, 2, and 3. So we will pick them. Once you pick an element in the first row, you cross out every element in that first row and every column that intersects with that element or that value you pick. Once you cross out, the remaining element will be 2 by 2. Then you write it down. For example, here, if you pick 1 first, if matrix A, you pick 1. Once you pick 1, you cross out 2, 3, and 4, 7. The remaining element is what? 5, 6, 7, 5, 6, 8, 9. That's why you have 1 that you pick. And then 5, 6, 8, 9. After that, you pick second element. And before you pick the second element, there's what we call a positional sign of a matrix. A matrix comes with a sign. Yes, the first value of a matrix is positive. The second value is negative. The third is positive. The next is negative. They are intersecting those signs. So any matrix you see, for example, now, like matrix A that is 3 by 3, the first position is what? The position of 1 has positive sign. They don't write it out. After that, you go to next is what? 3. Or next is 4. Anyone you want to go, is it 3 or 4? Then since the first one is plus, 2 should be next, you carry negative sign. 4 should carry negative sign. If you go that way now. So if you go the right hand side, the 1 will carry plus, the 2 carry negative, the 3 will carry plus. So that is how they are. So because we pick 2, we have to attach a sign, -2. That is why you see -2 here. Good. So if you pick -2, you cross the entire row that intersects with that 2. 1, 2, 3 will cross out. And what are going to be crossed out? 5 and 8 cross out. So the remaining item should be 4, 7, 6, 9. That's why you have 4, 7, 6, 9 there. Or do you need 4, 6, 7, 9? Same thing. You will pick the third element, which is what? 3. 3 should be positive. Once you pick 3, that means the entire row of that 3 will be cancelled, and the entire column of that 3 will be cancelled. The remaining thing should be what? 4, 5, 7, 8. That's why 4, 5, 7, 8 here. So this gives you 2 by 2 matrices now. And you now find the determinant of 2 by 2 matrices by what? Multiplying the diagonal element and subtract. If you do that now, you have that determinant is 0. That will be 0. So if you multiply that, for example, now you have 1. Okay, for example, you have here for example, this particular 3 now, it will be 4 times 8 minus 3 times 5. 4 times is what? 32. Minus 3 times 7 times 5 is 35. So 2 minus 35. That is it. For you write down that 2 minus 2, then and cross multiply the diagonal element and then subtract. Okay. We now access the second method. The second method is, I think some people say that one is easier because you don't do all this multiplication and finding of sign. What you do in second method is to write down the matrix in full. After writing down the matrix, you repeat the first 2 columns of that matrix and make it have 5 columns. For example, now, method 2, to evaluate this particular matrix, the determinant of this matrix now, what you do is you will write down the entire matrix. After writing down, you come and write the first column, which is A11, A21, A31 down, and also write the second column, A12, A22, and A32. After that, you look at the diagonal elements and pick them up for multiplication. So the diagonal elements you pick from top left corner to down right corner will be for addition. Then the ones you pick from down left corner to top right corner is for subtraction. Please go to the next page. Good. Practically, this is what I'm saying. See that matrix, A11, A2, A12, A23. That matrix now is used to expand what I'm saying. So you see rows have been written down. Additionally, the first two rows, I mean A11, A21, A31, and A12, A22, A32 has been repeated to make up 5 rows. To make up 5 rows. Now after to make up to have 5 columns, sorry, not 5 rows, 5 columns. So after having the 5 columns, what you do is to start picking the diagonal elements. Those elements that reach 3 by 3, because they were 3 by 3, those elements that reach 3 by 3, you cross them. Not that you're crossing them off, you are just crossing them because you want to pick them for multiplication. So the ones that you pick from top left corner to bottom right corner. For example, the one you pick from A11 to A32 here will be for addition. That's why you see A11, A22, A32 plus A12. So those are the elements that you pick from the top left corner to bottom right. Okay. After that, you just in short, it's just like finding matrix of 2 by 2. Yes, multiplying the diagonal of the face of the principal diagonal, and then subtract with those same diagonal bit of the left hand side. That's the same thing you are doing once you repeat the first 2 rows, so that the matrix of the first 2 columns, so that you have the 5 column now. Okay, we apply that method here. If you see here, we apply the method here to find a solution to the example now. So you have here matrix 7, 1 minus 3, it's 3 by 3. Now, how do you do that 3 by 3? You see, we have repeated the 3 by 3 here. But additionally, we now repeat 701 and 152. Okay, sorry, 15 minus 2. To make it 5 columns now. After that, now we pick by drawing lines so that we ensure we pick 3 elements of principal diagonals. So from 7 to 1 is the one I said, from the top left to the bottom right. Yeah, top left to bottom right. So if you pick, you draw a line. The first line will pick 751. Yeah. Second line pick 141. Third line pick 30 minus 2. You see? So those are the ones you multiply them out. So you multiply 751, 7 times 5 times 1, plus 1 times 4 times 1, plus 3 times 0 times minus 2. That is it. Plus. After that, you subtract the one you pick from bottom left to top right is the one you subtract. For example, you come here and pick 1 5 minus 3, we multiplied. 1 5 minus 3, we multiplied. Also multiplied 2 4 7, and also multiplied 1 0 1. Okay, those one we subtract. After that, you sum them up, you will have the answer. Please go to the next page. Next page. Go and lie down from me. Next page, please. Okay, yeah, we now go to minor and cofactor. We now go to minor and cofactor. I think this will be our last topic, minor and cofactor. If you have understood determinants, preferably from the perspective of the first method, you would not have any difficulty in finding minors. After all, those crossing off of rows that intersect with the elements you pick from a matrix are what you use for finding minors. So if you have understood or you have followed the first method of finding determinants, congratulations, because this one will be just a piece of cake for you. without explain so that you would follow up immediately. How you find minor is a minor is a determinant of a 2 by 2 matrix that you obtain from a 3 by 3 matrix when you cross off the row and the column associated with an element you have picked. For example, now for this matrix 1 minus 1 2, the matrix we use for example here, there are 9 different elements or 9 different entries. Yes, there are 9 entries. Hence, we will have 9 determinants. So we have 9 minors. Why will we have 9 minors? Because you will pick elements of the matrix, the resulting 2 by 2 matrix, and have their determinant. Okay, so what do? We pick an element for a matrix. After picking, we cross off the values from the row and column that touches that particular element you picked. If you cross it off, the result will be 2 by 2 matrix. That 2 by 2 matrix, just find the determinant. How do you find? Remember how we did it now? You multiply the diagonal element from top left to bottom right, and then subtract the one for bottom right too. So let's try here now. See what we do here. The steps are delete the I row and j column of a matrix. How do you delete them? By picking a matrix, by picking a value, you delete the row and column. And then compute the determinant of the remaining matrix after deleting the row and the column of step 1. That's what I have just explained now. So whether you're doing that or not, just take note of the process. Okay. After that, now you compute. For example, for this particular example now, we want to compute the minor M11. M11 is the minor you obtain when you pick the value of the matrix. You pick the value 1. If you pick value 1, you cross out the entire row, which is 1 minus 1 3. I'm sorry, 1 minus 1 2, and also cross out the entire row, which is 1 2 and minus 1, and the remaining will be 1. Okay, will be minus 1 1 minus 1. Good. So you find the determinant. How do you find the determinant? Will be minus 1 times minus 1 minus 1 times 1, which is 0. Next page. Next page. So the next thing will be you go and pick. Okay, the next thing will be you pick the second value. Once you pick the second value, you cross out the row and columns. You go again, pick the third value. You go again, pick the fourth value. Short, you will pick till you pick all the values in that matrix. Remember, for the determinant, we pick only three values. Is either you pick the first row, pick the second row, pick the third row, no problem. But for the minors are those elements associated with picking an element from a matrix and crossing off the row and column that is associated with that value matrix that we made them, and find out those determinants. You will obtain what we call the minors. Okay. Now, after obtaining the minors, you group them into a new matrix. We call that the matrix of the minors. And mostly, we can see here that therefore, the matrix of the minors given by capital. So we call that because it's a combination of the minors. This matrix that we obtain the cofactor, that the positional value or the positional sign has been attached. If you pick the sign of matrix and multiply by the minor, you have what we call the cofactor. For simplicity and clarity, I have put down how signs are distributed across position of a matrix here. For example, now you will see here that the positional sign of a 3 by 3 matrix, like I said, the first value of a matrix carries plus sign. And from that first value, and apply their signs. The reason being that the signs are intersecting. If the first cell is plus, the second must be negative. If the cell you are into is plus, the surrounding cells must be negative. That's what I mean. So since I said that in the first row and the first column, the first cell I'm talking about. If the first element is negative sign, so that's what I mean. Now, if you look at it here now, the cells should, and once the surrounding cell to that negative cell should be positive. That is it. So following that explanation, the positional sign is given by this plus negative plus negative plus negative. So if you carry this negative sign and multiply by the corresponding element, I mean the corresponding minor element, you have what we call the cofactor. I repeat, if you want to find the cofactors of the matrix you have obtained area, you just multiply the sign of the matrix by the corresponding element of the matrix of the minors. Okay, so go down. I think that will be the final page. Next page. Next page. Good. Finally here. The question says for the matrix, for this matrix minus 1 minus 1 2, that you should obtain what? Cofactor. This matrix is the same matrix we use to find the minors, so we will not face any stress. Remember, if there's any question you have that is asked to you, for example, if you are asked to find a cofactor of a particular matrix, the first thing you should do is to find the minors of that matrix. It is through the minors that you'll be able to find the cofactors. I think that's the only way I know. I don't know if there's another way around. That's the only way I know. So obtaining minors is a way of obtaining cofactors. So if you have already calculated the minors, the only thing you need to do to find the cofactor is do what? Multiply the elements of the matrix of the minors by the corresponding positional sign. Once you do that, you have the cofactor. For example, in this example we want to do now, we have already obtained the minors and the matrix of the minors. The matrix of the minors was given by M, which the first row contains 0 minus 3 3, and the second row contains 1 minus 3 minus 2, and the third row contains 1 3 1. So for you to obtain the cofactor here, what do? Multiply these values by the positional value, by the positional sign of a matrix. So for 0 here, 0 is 0. If you multiply by minus 1, so if you multiply 0 by 1, you will see the 0. That is why the cofactor here is denoted by C. So the computed cofactor here is by C. So C, the first element still remains 0. Why? Because 0 times 1 is what? 0. We go to the second element of the first row, which is 3. The second cell contains what? Minus 1. Contain minus 1, minus sign. So minus 1 times minus 3 is what? Is 3. Minus cancels minus. That's why it becomes 3 instead of minus 3 that it was previously. Okay, we go to the third element of the first row, which is 3. That cell contains which sign? Plus. So plus 1 times 3 is what? Still remains 3. So we work like that till we finish. For example, For example, like in the first element of the second row, which is -1, that particular cell carries what? -1, negative sign. So -1 minus 1 multiplied by 1 is what? 1. That is why the cofactor element of that row is 1. So this is where we end. We follow the same process to obtain the cofactor, okay, the matrix of the cofactor for that particular matrix. The another exercise here anyway. This idea says I should find a determinant, minus, and cofactor of the following square matrix. Remember, if I did not say it, a determinant can only be calculated from a square matrix. That is why in some books they say determinant of a square matrix. There's no other way. There's no way you can calculate determinant for a non-square matrix. So square matrices are what? That have what? Same row and column. Determinant of a square matrix not find determinant. In short, without being square matrix, you cannot even think about finding minor. You cannot think about finding inverse of a matrix that is not a square matrix. So square matrix is special case of matrix that we use in obtaining so many things. Okay. So for the following square matrix, what you are asked to do is to find the determinant. We have passed through that. We've explained how determinant can be obtained. And you are also asked to find the minors. You have just done that, how we obtain that. And lastly, you are asked to find the cofactor. We've just finished that cofactor. They are all very easy to obtain. So please go and try that. If you finish right, I don't know how you can just do that and send me the result you have. Let me just see how much you understand, because I cannot be shouting for nothing. Someone must understand. Okay, please. I think this should be the end. Yeah. Thank you very much. Next page anyway. Just try the exercise. Next page. Let me see what is there. Next page. Okay, the end. Thank you. Thank you very much, everyone out there. Without you, I wouldn't be here. I don't even have time to sleep, not to talk about sitting down to talk without an audience. So I thank you very much, every one of us that make this presentation possible. It's an opportunity for me to reach out to people based on what I know. I like teaching. So thank you very much, the listener. Those that will listen after this, thank you very much for wanting to learn. Thank you very much for reaching out to me to be one of the volunteers in this platform. I like learning. I am still a learner, and I like people to learn from me too. Okay, thank you very much. Thank you. Bye for now.
All right. Thank you very much, Ukobong. Thank you for devoting your time and taking us through this class. Actually, this is not the number of students we usually have in class. As a matter of fact, we have 2 classes running concurrently. One is on Teams. They also had business maths today. And over here, we're having Math 101, Logic and Linear Algebra, as the case may be. So, but we did encounter a challenge at the other end of the class, because today's network was very frustrating. As a matter of fact, we had to reschedule the other class because network connectivity was difficult for the lecturer from that other end. So it's, I guess it also affected the number of students we have in class today. We could see sometimes it would go up to 12, as the case may be, and then it would drop again. So today's network connectivity was quite bad. And sometimes even in your speech, it's also lagging somehow, but we were able to hold on to it. So the network challenge today was really at the extreme, but thank you so much for driving through to the end of the class today. And
so
yes,
I hope I can go for now.
Yes, you can. So for those who are not on the call, we would upload this and share.
All right, bye-bye.
All right. We will upload this and share on our YouTube channel and let everybody watch. So thank you very much, Ukobong, for being with us today. We hope to see you again next week for the second class, right? So thank you everyone on the call so far. I can still see Ifeoluwa and Devon. Thank you for being here in class. The assignments will be shared on the WhatsApp community, so you can attempt it. and we would share the email address where you would send the assignment or submit the assignment to, and then we would have it extended to the lecturer to take a look at, and he would quickly address your responses in the class next week before we kick off with the class for the day come next Saturday. So thank you very much, everyone, for being on the call, and do have a wonderful, wonderful weekend ahead. Stay happy and stay blessed as always. Thank you.